The EPR paradox, named after Albert Einstein, Boris Podolsky, and Nathan Rosen, is one of the most intriguing and perplexing paradoxes in the foundations of quantum mechanics. In 1935, Einstein and his colleagues formulated this thought experiment to highlight what they saw as the puzzling implications of quantum theory. The core of the paradox lies in the concept of quantum entanglement, a phenomenon where two particles become correlated in such a way that the state of one particle is directly related to the state of the other, even if they are separated by vast distances in space. The paradox begins with the premise that if two particles are entangled, then measuring one particle's property, say its spin or polarization, immediately determines the property of the other, regardless of how far apart the particles are. In the classical worldview, this seems impossible. How can information about one particle instantaneously affect another particle, seemingly violating the principles of special relativity, which states that no information can travel faster than the speed of light? To Einstein, this was spooky action at a distance, something he believed was incompatible with the nature of physical reality. But the paradox goes deeper. In quantum mechanics, when two particles are entangled, their individual properties aren't well defined until they are measured. This means that before the measurement, the particles are in a superposition of all possible states. Only when the measurement is made does the particle choose its state, and this choice is seemingly correlated with the measurement made on the other entangled particle, regardless of the distance between them. The EPR thought experiment imagines two entangled particles being separated by an enormous distance. If a measurement is performed on one particle, the outcome will instantaneously influence the other particle, even though no signal can travel faster than light. This suggests that either the particles have some pre-existing hidden variables, information about their state that was determined prior to the measurement, or that quantum mechanics, as Einstein feared, was incomplete in its description of reality. In other words, there might be more to reality than the probabilistic framework offered by quantum mechanics. This dilemma raised questions about the locality of physical theory, whether objects are only influenced by their immediate surroundings, and the role of hidden variables in quantum mechanics, which could provide a more intuitive deterministic explanation for quantum phenomena. The EPR paradox sparked a long-standing debate between two competing views of reality: the Copenhagen interpretation, which embraces the probabilistic nature of quantum mechanics and its apparent non-locality, and the hidden variables theory, which seeks a more classical, deterministic description of the universe. This tension between the two perspectives would persist for decades. But then came the groundbreaking work of John Bell in the 1960s, who formulated Bell's theorem, which showed that if hidden variables were to explain quantum correlations, they would have to defy certain principles of physics, particularly the principle of local realism, which holds that objects are only directly influenced by their immediate surroundings, and that information cannot travel faster than light. Bell's theorem led to experiments that could test the validity of hidden variables, and over the years, experiments have overwhelmingly confirmed the predictions of quantum mechanics, showing that the phenomenon of entanglement does not require hidden variables, and that the instantaneous correlations between entangled particles are real. Thus, the EPR paradox challenged our most fundamental assumptions about the nature of reality, showing that quantum mechanics forces us to reconsider deeply ingrained concepts of locality, causality, and information. However, while quantum entanglement is well established experimentally, the EPR paradox remains a source of philosophical intrigue. It raises questions about the completeness of quantum mechanics and the nature of the universe itself. Does quantum mechanics provide a complete description of reality, or are there deeper layers of reality still hidden from view? Can we ever truly reconcile the strange non-locality of quantum entanglement with our classical intuition of space and time? The EPR paradox invites us to rethink the very fabric of reality. It challenges our ideas about how information travels, how objects are connected, and even how we define what is real. While quantum mechanics offers a powerful and successful theory for understanding the microscopic world, the EPR paradox serves as a reminder that there may always be deeper, more mysterious aspects of the universe, waiting to be uncovered through the relentless pursuit of knowledge. It is a paradox that continues to inspire wonder and curiosity, reminding us that even the most counterintuitive ideas can lead to profound insights about the nature of existence. Mathematical illusions of certainty. is a fascinating and somewhat paradoxical concept that explores the tension between the seemingly unshakable certainty of mathematics and the inherent limitations and uncertainties embedded within mathematical reasoning itself. At first glance, mathematics may appear to be a realm of absolute certainty, where proofs and theorems are rigorously derived from axioms and the results follow with unerring precision. However, upon closer inspection, there are many instances where mathematics reveals surprising illusions of certainty, leading us to question whether absolute certainty is ever truly attainable. One of the most prominent examples of this phenomenon is Gödel's incompleteness theorems, which shook the very foundations of mathematics in the 20th century. Gödel showed that in any sufficiently powerful formal mathematical system, there are true statements that cannot be proven within the system itself. In other words, no matter how carefully we construct a mathematical system, such as number theory or geometry, there will always be true facts that lie beyond its reach. This implies that mathematical certainty is never complete. There will always be limits to what we can know, even within the seemingly airtight world of logic and proof. This inherent limitation is a stark contrast to the idealized notion of mathematics as a field of absolute, unquestionable truth. In many areas of mathematics, we think we have arrived at a complete understanding, only to discover later that something has been overlooked, or that a previously proven result was based on flawed assumptions or an incomplete model. This tension between the appearance of certainty and the reality of uncertainty lies at the heart of many mathematical illusions. Another striking example of mathematical illusions of certainty comes from probability theory. At first, probability offers a reassuring sense of predictability, especially in contexts like gambling, weather forecasting, or statistical analysis. Given enough data, probability theory suggests that we can predict outcomes with a high degree of certainty. However, beneath this surface of certainty lies the ever-present uncertainty principle, where even the best predictions can be subject to significant fluctuations and anomalies. The Monty Hall problem, for example, is a well-known probability puzzle that demonstrates how human intuition often conflicts with probabilistic logic. When faced with 3 doors, behind one of which is a prize, most people believe that switching doors after one is revealed doesn't affect their chances. But in reality, the optimal strategy is to always switch, as probability theory dictates that doing so increases the odds of winning to 2/3, compared to the initial 1/3 chance of choosing correctly. This seemingly paradoxical result reveals how our intuitions about certainty can be wildly misleading, even when we think we understand the odds. Similarly, the birthday paradox illustrates another mathematical illusion of certainty. Intuitively, most people believe that the probability of 2 people sharing a birthday in a group of 23 is low. After all, there are 365 days in a year. But in reality, the probability is over 50%, which seems counterintuitive. This illusion arises because the birthday paradox doesn't ask about the probability of a specific person sharing a birthday with another, but rather the probability that any 2 people in a group will share a birthday. The mathematics behind this problem relies on the fact that as the number of people in a group increases, the number of possible pairings increases exponentially, which rapidly increases the probability of a shared birthday. Mathematical illusions also arise when we encounter paradoxes like Benford's law. This law, which states that in many sets of real-world data, the first digit is more likely to be small, such as 1, 2, or 3, than large like 8 or 9, appears at first to be a simple, almost trivial observation. Yet its implications are far-reaching, suggesting that there is an underlying mathematical order to seemingly chaotic datasets. Benford's law has been used in forensic accounting to detect fraudulent data, and has applications in various fields, from physics to finance. The paradox lies in the fact that this statistical law applies to datasets we often don't expect it to, challenging our assumptions about randomness and certainty in the real world. Moreover, paradoxes in infinity also illustrate the mathematical illusions of certainty. Take, for instance, Hilbert's hotel, a thought experiment that demonstrates how infinite sets behave in ways that defy our intuition. In Hilbert's hotel, an infinite hotel with an infinite number of rooms, each room occupied, can still accommodate new guests by moving each occupant to a different room, making space for an additional person. This result seems absurd in the context of finite hotels, where an occupied hotel with no vacancies cannot accept new guests. Yet in the infinite realm, such seemingly impossible situations become mathematically possible. This paradox forces us to reconsider our understanding of infinity and how it challenges our very concept of certainty in mathematics. Even Cantor's diagonal argument, which shows that the set of real numbers is uncountably infinite and cannot be matched one-to-one with the set of natural numbers, reveals a mathematical illusion of certainty. Our conventional understanding of numbers is shaken when we encounter this result, as it seems to violate the principle that more numbers should always be possible to count. Cantor's argument proves that infinity is not simply one big homogeneous quantity, but comes in different sizes, and some infinities are larger than others. This revelation confronts us with the surprising, unsettling realization that even in the world of numbers, the very notion of infinity holds secrets that our intuition struggles to comprehend. Mathematics, at its core, is a discipline that strives for precision and certainty. And yet paradoxically, the deeper we dig, the more we realize that even the most rigorously defined systems are full of illusions, where certainty is often a mirage. Whether it's Gödel's incompleteness theorems, paradoxes in probability, or the counterintuitive nature of infinity, mathematics constantly challenges our assumptions about certainty. It reveals that even in a realm we consider to be the pinnacle of logical truth, there are surprises waiting to be uncovered, subtle, complex, and sometimes bewildering. Braess's paradox is a fascinating and counterintuitive phenomenon that appears in the world of traffic flow and network theory, where adding a new route or improving existing roads can actually worsen traffic congestion. On the surface, it seems entirely logical that adding another route to a busy road network should ease congestion. But Braess's paradox shows that this isn't always the case. Sometimes, it can have the opposite effect, leading to even longer travel times for everyone involved. The paradox was first formulated by the mathematician Dieter Braess in 1968. Imagine a city with a network of roads and several routes that drivers can take to get from point A to point B. Each driver is assumed to choose the fastest route, based on the travel time of each option, with the goal of minimizing their own time. In an ideal world, more roads would mean more options, and thus faster travel times for everyone. But in the strange world of Braess's paradox, adding a new road or lane can cause all drivers to adjust their behavior in such a way that the overall system becomes less efficient. To better understand this, picture a simple network. There are two main roads, each with a certain travel time depending on the level of traffic. When the traffic load is light, the system works fine. But when an additional route is introduced, say a shortcut, everyone starts using this new route, assuming it will speed things up. However, the introduction of this shortcut doesn't actually benefit the system as a whole. The added route leads to a situation where everyone's individual choices end up making the overall traffic flow worse, causing longer delays for all drivers. This paradox highlights a key concept in game theory called the Nash equilibrium, where each individual makes the best decision they can, given the decisions of everyone else. At this equilibrium, no one can improve their own situation by changing their behavior. In the context of Braess's paradox, each driver assumes that taking the new shortcut will reduce their travel time. But when everyone adopts this strategy, it leads to congestion on the new road, slowing everyone down. The net result is a system where the best individual decisions collectively lead to a worse outcome. What's truly surprising about Braess's paradox is that it works even if all drivers are acting rationally. The paradox doesn't rely on any irrational behavior or poor decision-making. In fact, it's the very fact that everyone is trying to act in their own best interest that leads to the collapse of the traffic network. Adding a new road, something that seems like an obvious improvement to a network, can actually make the overall system more inefficient. This phenomenon has been observed in real-world traffic systems, though it's often hidden beneath the complexities of actual road networks. In fact, Braess's paradox has been tested and confirmed in various traffic models and simulations. There are even some instances where road authorities have removed certain roads or altered traffic patterns based on the paradox to improve overall traffic flow. In one famous case, a road in the city of Düsseldorf, Germany was closed temporarily, and after doing so, traffic in the area improved significantly, proving that the original setup was creating unnecessary congestion. The paradox also extends beyond just roads and traffic. It has applications in network theory and optimization problems, particularly in situations where resources are shared, like telecommunications networks or even power grids. In these contexts, the paradox illustrates that adding more resources or routes doesn't always improve the overall system. In fact, it might make it worse by disrupting the delicate balance of how different parts of the system interact. What's particularly striking about Braess's paradox is that it challenges our intuition about how systems should work. We tend to think that more resources, more roads, more lanes, more options will lead to better outcomes. But in this case, the addition of more options doesn't always lead to an improvement. Instead, it can create new problems that were never anticipated, as individuals acting in their own self-interest can unintentionally cause a worse outcome for everyone. It serves as a reminder that complex systems, whether they're road networks or social systems, don't always behave in ways that align with our everyday expectations. In fact, adding complexity can sometimes reduce the efficiency of the system as a whole. The key takeaway from Braess's paradox is that the best individual choices aren't always the best collective choices. When individuals optimize their own paths without considering the impact on others, the entire system can break down. The paradox highlights the importance of cooperation and system-wide thinking when managing complex networks, and it suggests that sometimes the solution is to remove rather than add resources to a system. In the world of mathematics and optimization, Braess's paradox serves as a powerful example of how self-interest and individual optimization can lead to unexpected, and often counterproductive, results. It reminds us that the whole can be less than the sum of its parts, and that sometimes, the best solution is one that requires everyone to rethink their own strategies for the greater good. It's a subtle but profound lesson in how the dynamics of a system can behave in ways that defy our everyday intuitions. The mathematics of music and emotions might sound like an unusual combination at first. Math and emotions seem like such distinct realms. But when you take a closer look, you'll find that the relationship between music, emotion, and mathematics is surprisingly deep and intricate. Music is often thought of as an art form, full of beauty and feeling, but underlying all the melodies, harmonies, and rhythms is a vast world of mathematical structures. These structures not only shape the sound of music, but also play a significant role in how music influences our emotions. At its core, music is based on mathematical concepts such as frequency, rhythm, and ratio. The foundation of most musical systems relies on the concept of vibration. Sound itself is a vibration that travels through the air, and the frequency of those vibrations determines the pitch of the sound we hear. The mathematical relationship between different pitches creates the structure of scales and chords, which are the building blocks of music. For example, the intervals between notes in a major scale like the famous do-re-mi from The Sound of Music are based on simple ratios. The interval between the first and the second note is a whole step, which corresponds to a ratio of 9/8 in terms of frequency. The interval between the first and the fifth note, the perfect fifth, is in the ratio of 3/2, which gives the chord its harmonic stability. These ratios aren't just theoretical. They are directly tied to the way our ears perceive sound. Our brain is wired to respond to these specific patterns, which is why we find certain combinations of notes more pleasing than others. But it doesn't stop there. The way we experience emotion in response to music is also closely tied to mathematical structures. Take for example the idea of rhythm. Rhythmic patterns, especially those that repeat or follow a predictable pattern, play a huge role in how music makes us feel. When we listen to music, our brain tends to anticipate the next beat or the next phrase, and when it aligns with what we expect, it creates a sense of comfort and pleasure. However, when the rhythm is irregular or syncopated, it can create feelings of surprise or excitement. This is not just a psychological phenomenon, it's a mathematical one, as these rhythmic patterns can be understood as sequences of time intervals, and how those intervals relate to one another determines the emotional impact of the music. Beyond rhythm, the dynamics of music, how loud or soft the music is at any given moment, also involves mathematical principles. The volume of sound is a result of the amplitude of the sound waves, and changes in amplitude follow certain patterns that correspond to emotional responses. A sudden crescendo, where the music gradually becomes louder, often signals the building of tension or excitement. A decrescendo, where the music gradually softens, often leads to a sense of release or resolution. These patterns have a direct connection to the way our brain processes and reacts to sound waves, which in turn influences how we experience emotion in response to music. Perhaps one of the most fascinating intersections of math and emotion in music is the concept of harmony. Harmony, the combination of different musical notes played simultaneously, is deeply rooted in mathematical ratios. When we hear harmonious chords, like a major chord or a minor chord, we are actually hearing notes whose frequencies relate to each other in simple, elegant ratios. A perfect octave, for example, is the ratio 2:1, meaning the second note vibrates at twice the frequency of the first note. This ratio is often described as pleasing or pure to our ears, and it's found in many musical traditions around the world. On the other hand, dissonant chords, those that sound tense or unstable, are made up of frequencies that are less harmonious in their ratios. These dissonances create a sense of tension or unease, and it is this tension that composers often use to create emotional complexity in their music. The connection between emotion and music can also be explained through the idea of fractal patterns. In mathematics, fractals are structures that repeat themselves at different scales, creating a sense of infinite complexity. When we listen to music, especially in genres like classical or progressive rock, we often hear a recurring motif or theme that is expanded and developed over time. These patterns mirror the fractal nature of music. What seems like a simple melody can unfold into something much more complex and emotionally resonant, just as a fractal shape reveals greater intricacies the deeper you look. The emotional impact of music also ties into mathematical modeling of how we process sound. Research in neuroscience has shown that certain patterns in music can trigger specific emotional responses because they correspond to the brain's reward systems. For example, a musical resolution, where a dissonant chord resolves to a consonant one, releases dopamine in the brain, the same neurotransmitter involved in the feeling of pleasure. Similarly, studies have shown that music with a fast tempo or a major key tends to evoke feelings of happiness or excitement, while music with a slow tempo or a minor key often leads to feelings of sadness or contemplation. These patterns can be modeled mathematically by analyzing the relationships between the frequency and duration of the notes, and how those interact with our brain's wiring to elicit an emotional response. What makes the mathematics of music and emotions so beautiful is that it reveals a deep symmetry between the logical structures of math and the way we experience the world. Music may appear to be an art, driven by creativity and feeling, but behind the scenes, it's guided by a set of mathematical principles that we have come to understand over centuries. These principles, whether it's the frequency ratios in harmony, the rhythmic patterns in time, or the fractal-like structures in composition, allow music to touch us on a profound emotional level. It's almost as if music is a universal language that speaks directly to our emotions, using the abstract language of mathematics as its medium. When you think about it this way, it becomes clear that music isn't just about notes and rhythms, it's about how those notes and rhythms are organized in a way that mirrors the very structures of the universe. It's a reminder that math and emotion aren't opposites, they're intertwined, with one enriching and amplifying the other in ways that are both logical and deeply human. The Doomsday Argument is one of the most mind-bending and unsettling thought experiments in probability theory. It's an argument that uses statistics and reasoning about the future to make predictions about the likelihood of human extinction. The paradoxical nature of the argument lies in how it seems to suggest that the probability of humanity facing an impending doom could be much higher than we would expect, even though we might have no direct evidence of such an outcome. At its heart, the Doomsday Argument revolves around a concept called the anthropic principle, which says that when we try to predict the future or understand our place in the universe, we must take into account the fact that we are part of the process we're studying. In simpler terms, the idea is that because we exist, we must consider the likelihood of our existence when making predictions about the future of humanity. The argument was first formulated by the philosopher John Leslie in the 1980s and later refined by others, including Nick Bostrom. It's rooted in probability theory and attempts to answer the question, how likely is it that humanity will experience a catastrophic event in the near future, based on what we know about the past. To explain the argument, imagine we are a randomly selected member of all humans who will ever live. The basic idea is that we are not in a particularly unique position in the timeline of humanity. If there have been many generations of humans, and many more are to come, we would expect to find ourselves somewhere near the middle of all human existence. If we find ourselves living in an era with a large population, it might suggest that the total number of humans who will ever live is quite large. However, if humanity is nearing its end and there are only a few generations left to go, our position would be closer to the end of the timeline. To put it more concretely, the Doomsday Argument relies on the principle of indifference, which says that all possibilities should be considered equally likely unless there's a reason to believe otherwise. In the context of the Doomsday Argument, this means that our position as living humans in the timeline of humanity is as likely as any other position. So, when we observe how many humans have lived so far, we can make an educated guess about how many humans will live in the future. If we find ourselves among the early generations of humans, the argument suggests that humanity might be much closer to its end than we'd like to think. This reasoning leads to an unsettling conclusion. If we are in the middle of human history, then we may be nearing the end of humanity's existence. The argument suggests that if there are many more humans who will live in the future, it's statistically unlikely that we would be born at a time far from the end. In other words, if we're here in the present, the future must be limited, and the possibility of catastrophic events that lead to human extinction is greater than we tend to believe. This conclusion doesn't mean that the world is definitely going to end soon, but rather that it might be more probable than we'd expect, simply based on the probability of where we are in the timeline of humanity. The argument is designed to challenge our intuitions about the future, suggesting that humanity might be closer to extinction than we realize, even though we don't have direct evidence to support that idea. Now, there are a lot of debates surrounding the Doomsday Argument, and not all scientists and philosophers agree with it. One criticism is that the assumptions behind the argument, such as the idea that we are a random sample of all humans who will ever live, might be flawed. After all, it's possible that our current existence could be more or less likely depending on factors that aren't accounted for in the argument. Some critics argue that the Doomsday Argument is too simplistic because it treats the timeline of humanity as though it were entirely predictable, ignoring the complexities of human development, technological progress, and societal changes. Others criticize the argument for being too deterministic, as if the future is already written based on our position in the present. This line of thinking doesn't account for the potential of human creativity, resilience, and the ability to shape the future in ways that might prevent disaster. But even if we don't fully accept the Doomsday Argument in its entirety, it raises important questions about how we think about the future of humanity. It's a reminder that we don't know as much as we think we do about what's coming next. Just because everything seems stable today doesn't mean it will remain that way indefinitely. It challenges us to think about the long-term survival of our species, and the risks we face in the future, and to consider the unpredictable nature of the universe and human progress. The Doomsday Argument also ties into bigger philosophical questions about probability, uncertainty, and humanity's place in the universe. It asks us to consider how much we can really know about our future, and whether the future of humanity is more precarious than we typically believe. While it doesn't predict the end of the world, it does make us question how we can navigate our future in a world where uncertainty about what lies ahead is always lurking. In a way, the Doomsday Argument isn't about predicting doom, it's about making us think more deeply about our existence in the grand scheme of things, and how little we truly know about the future. It's a humbling thought experiment, one that invites us to consider the fragility of humanity, while also reminding us that probability and uncertainty are constant companions in the journey of life. It's a paradoxical and unsettling reminder that as we look to the future, we might not be as far from our end as we might like to believe. Quantum immortality and probability is one of those mind-boggling ideas that stretches our understanding of life, death, and the nature of reality itself. It's based on a thought experiment in quantum mechanics, which is the branch of physics that deals with the behavior of particles on the tiniest scales, things like atoms and subatomic particles. To make sense of it, we need to dive into a concept called the many worlds interpretation of quantum mechanics, and from there, we'll explore what it might mean for something as profound as immortality. To start, let's think about quantum mechanics, and how it challenges our everyday experience of the world. At the quantum level, particles don't have definite positions or velocities until they're measured. Instead, they exist in a state of superposition, meaning they can be in multiple states at once. When you measure them, they collapse into one specific state, but before you measure them, they can exist in many different possible outcomes simultaneously. It's like flipping a coin and having it both heads and tails at the same time until you observe it. Now the many worlds interpretation suggests something even wilder. Instead of a particle's state collapsing into one definite outcome, every possible outcome of a quantum event happens, but in separate, non-communicating parallel universes. This means that every time a quantum event occurs, the universe splits into different branches, each one corresponding to a different outcome. In other words, the many worlds interpretation imagines an infinite number of parallel universes, each one containing a different version of you, experiencing a different set of outcomes. This brings us to quantum immortality, which is an intriguing extension of this idea. Quantum immortality suggests that, in certain scenarios, a person could never die. Let's break it down. Imagine you're in a life or death situation, like you're playing Russian roulette. In a classical view of the world, there's a probability that you'll survive, and a probability that you won't. But in the quantum world, things behave differently. Every time you pull the trigger, there are two possible outcomes. You either survive or you die. According to the many worlds interpretation, both outcomes happen, but in separate universes. So in one universe, you survive, and in another, you don't. But the key idea here is that from the perspective of you, the observer, you'll always find yourself in the universe where you survive, because your consciousness can only follow the branch where you're still alive. It's almost like you're quantumly immortal. No matter how many times you face a life-threatening situation, there will always be at least one universe where you survive, so your conscious experience will never truly end. The death you might expect to experience in one universe is offset by the fact that in another universe, you're still alive. As strange as it sounds, the probability of your own death becomes zero in the context of quantum immortality. Every time you face death, there's always an infinite number of universes where you survive. But this idea is not without its problems and paradoxes. The most significant issue with quantum immortality is that it doesn't fit well with our understanding of consciousness. If you're always experiencing the universe where you survive, what does that mean about death and the nature of consciousness itself? After all, if you're alive in one universe, but not in another, how do you experience that? The very concept of immortality in the quantum sense seems to raise more questions than answers. Furthermore, there's the issue of probability. While the many worlds interpretation suggests that every possible outcome happens in some universe, it doesn't guarantee that you will always be in a universe where you survive. The likelihood of quantum immortality doesn't take into account how the physical world works on the large scale. Quantum mechanics dominates the microscopic world of particles, but once we move to the scale of human life, the classical world, where things like aging, illness and accidents happen, dominates. And there are many factors in play that make the idea of quantum immortality more speculative than scientifically plausible. Still, quantum immortality is a fascinating thought experiment because it challenges our understanding of death, probability, and the universe itself. It forces us to consider the idea that our lives could be part of an infinitely branching multiverse, where death in one reality is simply a transition to another reality, where we continue to exist. It's as if the rules of probability and fate bend in such a way that from a personal experience perspective, we might never truly experience the end. Of course, it's important to note that the many worlds interpretation and quantum immortality are not universally accepted. Many physicists prefer alternative interpretations of quantum mechanics, such as the Copenhagen interpretation, which does not require the existence of parallel universes. In the Copenhagen view, the wave function collapses into a single outcome when it is measured, and there's no need to invoke multiple universes. Additionally, the idea of quantum immortality has been criticized for being overly speculative and lacking empirical evidence to support its claims. Yet, despite these criticisms, quantum immortality taps into a deeper curiosity about the nature of existence and consciousness. It asks us to think about the boundaries between life and death in a way that modern science hasn't fully explained, and it makes us reflect on the role of probability in shaping our reality. Could there be a universe where we always survive, no matter the odds? Could our consciousness be linked to an infinite number of parallel worlds? These are the questions that quantum immortality poses, And even though the theory is unlikely to be proven in the near future, it invites us to consider the strange and wonderful ways that probability and quantum mechanics might reshape our very understanding of existence. The paradox of the heap is one of those deceptively simple philosophical puzzles that can make your mind spin when you dig into it. At first glance, it seems like a problem about language, but it also challenges our understanding of concepts like gradual change, vagueness, and categories, things we usually take for granted. This paradox is rooted in what's called a Soreitz paradox, which comes from the Greek word soros, meaning heap. The paradox deals with the idea of vague predicates, terms like heap, bald, or tall, that don't have sharp, clear-cut boundaries. The paradox begins with a seemingly innocent question. When does a collection of grains of sand become a heap? Imagine you have a single grain of sand. It's clearly not a heap. Now, if you add a second grain, it's still not a heap. What if you keep adding grains one by one? At what point do you stop and say, okay, now that's a heap? The problem is, as you add grains of sand, it's hard to pinpoint the exact moment when the collection crosses over from not a heap to a heap. The issue is that there doesn't seem to be a precise number of grains that makes something a heap. At some point, you have a heap. But where do you draw that line? The paradox of the heap really pushes us to question how we use vague terms like heap. In everyday life, we make these distinctions all the time. Yet there's no clear-cut rule for when one thing turns into another. This is what makes the paradox so intriguing. It shows that our concepts of things like size, quantity, and category don't always fit neatly into the black and white logic we'd like them to. If we insist that adding one grain of sand at a time never creates a heap, then we're led into a situation where, after adding 1,000 grains, we're still saying it's not quite a heap, which feels absurd. Yet, at the same time, we can't say that the collection of sand grains is automatically a heap once it reaches a certain number, because there's no definitive line. What makes the paradox of the heap even more fascinating is that it applies to a wide variety of situations beyond just grains of sand. It's about gradual changes in general. If you think about baldness, for instance, it's hard to say exactly how many hairs someone has to lose before they're considered bald. If one hair doesn't make a difference, does it take 2 or 5? At what point do you go from not bald to bald? Similarly, consider the question of when a pile of leaves becomes a heap of leaves. The paradox shows us that many concepts in life don't have exact boundaries. They blur at the edges, and this vagueness can lead to contradictions. There's also a deeper, more philosophical layer to the paradox of the heap. It challenges the idea that we can always define things in clear, precise ways. It asks us to think about how we categorize things, and whether our categories should always be rigid. In fact, the paradox suggests that sometimes, our understanding of the world may need to be more flexible. After all, how we use language is not always governed by absolute logic. It's shaped by social conventions, common sense, and context. The key insight from the paradox of the heap is that our everyday concepts might not fit into neat logical boxes. If we take the paradox seriously, it teaches us that gradual changes, especially in contexts involving vague or imprecise terms, don't always fit into the structure of formal reasoning. It's a reminder that life often doesn't conform to the rules of strict definitions and categories, and we have to navigate the world with some tolerance for ambiguity. One way to approach the paradox is to think about the role of borderline cases, situations where it's just not clear whether something belongs in one category or another. These cases are what the Soreitz paradox calls into question. If you accept that there's some level of indeterminacy in how we classify things, you might reach the conclusion that the very idea of a heap is a continuum, and that's why it's so hard to define. The line between heap and not a heap isn't so much a sharp boundary as it is a gradual transition. Some philosophers and logicians have tried to resolve the paradox by introducing degrees of truth or fuzzy logic, which allows for concepts to be somewhat true or somewhat false, depending on context. For example, instead of saying this is a heap, or this is not a heap, we could say this is partially a heap, or this is more heap-like than not. This approach helps us navigate the vagueness in language without forcing us to make arbitrary cuts between categories that don't have natural boundaries. In the end, the paradox of the heap doesn't really have a solution in the traditional sense. It's more of an exploration into the limits of our understanding of concepts and language. It shows us that sometimes, our categories and definitions aren't as precise as we'd like them to be, and that's okay. Life is full of gray areas, and this paradox helps us confront the fact that not everything fits perfectly into the boxes we try to put them in. The Burali-Forti Paradox is one of those mind-twisting logical puzzles that emerges from the strange world of set theory. And it's a perfect example of how sometimes seemingly simple concepts can lead to deep, profound contradictions. Named after the Italian mathematicians Giuseppe Burali-Forti, this paradox arises when we start to consider the idea of infinite sets and the way they interact with each other. It's a paradox that challenges our understanding of infinity, something that seems both simple and impossibly complex at the same time. To understand the Burali-Forti paradox, let's first think about ordinal numbers. Ordinal numbers are a way of organizing and counting sets of objects, especially when those sets are infinite. While natural numbers 1, 2, 3 help us count finite quantities, ordinals are used to describe the order of elements in an infinite set. For example, we can think of the set of all natural numbers as being ordered in a sequence, starting from 1 going to 2 and so on. But in the realm of ordinals, there's no largest number. There's always another number you can add. In fact, ordinals extend infinitely, and the set of all ordinals forms what we call a well-ordered set, a set where every subset has a smallest element. Now the paradox arises when we consider the idea of the largest ordinal. According to the laws of ordinal arithmetic, if you have an infinite set of ordinals, you can always create a new ordinal by adding one more to the end. So it would seem that there's no largest ordinal, because you can always keep adding to the sequence. But here's where things get tricky. The Burali-Forti paradox shows that when we assume the existence of the largest ordinal and attempt to place it within the structure of the set of all ordinals, a contradiction emerges. The paradox begins with the idea that we can create a set that contains all ordinals. This would be a massive all-encompassing set, one that contains every ordinal number you could ever imagine. But here's the problem. When you attempt to assign an ordinal to this set of all ordinals, you run into a dilemma. The set of all ordinals should have an ordinal greater than any individual element in the set, but because it contains every ordinal number, including all those larger than the ones before it, it leads to an infinite regression. There's no way to define the largest ordinal without creating an infinite loop of ordinals that seem to contradict each other. What's particularly bizarre is that this paradox is not just a small glitch in logic, it's a fundamental issue in how we define and think about infinity. The Burali-Forti paradox reveals that if we try to treat the set of all ordinals as a normal set, it leads to logical chaos. The idea that there could be a largest ordinal seems to contradict the very notion of ordinality itself. In other words, we can't have a largest ordinal, and yet trying to avoid this conclusion results in the paradox. It's a paradox that seems to suggest that our intuitive ideas about infinity might be fundamentally flawed or at least incomplete. This paradox also has deep implications for our understanding of set theory. Set theory, the mathematical study of sets, collections of objects, is foundational to much of modern mathematics, and it relies heavily on concepts like ordinals and transfinite numbers. The Burali-Forti paradox shows that in certain formulations of set theory, there are contradictions that arise when you try to form a set of all ordinals, leading to the need for more careful definitions and frameworks. One way mathematicians have dealt with this paradox is by adopting the concept of class theory. In class theory, instead of treating the set of all ordinals as a set, which would lead to the paradox, we treat it as a proper class, a collection that is too large to be a set, and therefore doesn't lead to the contradictions we see in the paradox. By making this distinction, we avoid the paradox, but it forces us to rethink how we handle the infinite. Another approach is to refine the way we define infinity itself. The paradox illustrates that simply assuming infinity works the same way for all sets, or that there's always a largest element, leads to contradictions. As a result, mathematicians have had to develop more nuanced views of infinite sets and how they relate to one another. These refinements allow us to navigate the complexities of infinite structures without falling into paradoxes like Burali-Forti. Ultimately, the Burali-Forti paradox is a reminder that infinity isn't just a big number. It's a concept that defies our normal ways of thinking about numbers and order. It pushes us to reconsider how we define and work with infinite sets in mathematics. It also challenges our intuition, showing that even in a field as precise and structured as mathematics, there are still areas where our understanding can unravel when we push too hard against the boundaries of what's possible. This paradox doesn't just throw a wrench in the gears of set theory. It also underscores the delicate nature of mathematical definitions. The very foundations we take for granted, such as the idea that sets can be well ordered or that ordinals follow a predictable progression, can sometimes collapse when we try to extend them to the infinite. And yet, even within this contradiction, mathematicians continue to find new and elegant ways to understand and manipulate infinity, showing just how flexible and resilient mathematical thinking can be in the face of the unexpected. The Grue and Bleen paradox is a thought experiment that stretches our understanding of inductive reasoning and philosophy of science, challenging our intuitions about how we form beliefs based on evidence. It was first introduced by the philosopher Nelson Goodman in 1955. And it explores the oddities that arise when we try to make predictions about the future based on past observations, particularly in the context of inductive logic. The paradox revolves around two newly coined terms, Grue and Bleen. To understand this, let's break it down. Imagine you're observing a series of emeralds, and you notice that all the emeralds you've encountered so far have been green. Based on these observations, you would predict that the next emerald you encounter will also be green. And this prediction would be reasonable according to the principles of inductive reasoning, which states that future events will resemble past ones. However, Goodman proposes an alternative hypothesis. What if instead of calling the emeralds green, we call them Grue? Here's the twist. Grue refers to emeralds that are green if observed before a certain time, but blue if observed after that time. The term Bleen is just as mind-bending. An emerald is considered Bleen if it is blue when observed, but green if it has not been observed yet. The paradox arises because we are faced with the question, why do we prefer to call emeralds green and not Grue? And why do we call them blue when observed but not Bleen? Both are logically consistent with the past observations we've made, but they lead to different conclusions about the future. Here's the crux of the paradox. Both the green to Grue transition and the blue to Bleen transition are based on the same observations and evidence. We've observed nothing but green emeralds, so based on the strict patterns of inductive reasoning, we should be able to predict that the next emerald will be either Grue, if we're working under the Grue hypothesis, or green under the more familiar assumption. But Goodman challenges our justification for favoring green over Grue. Why is the concept of green so much more acceptable to us than Grue, even though both are logically equivalent in predicting future observations? The paradox invites us to question how we define and justify terms, and how these definitions affect the way we predict and reason about the world. Goodman's paradox goes even further, forcing us to reconsider how we deal with generalization in science. Normally, we assume that our past experiences should guide our expectations for the future. But the Grue and Bleen paradox raises the uncomfortable possibility that this approach may not be as reliable as we think. If both green and Grue predictions are valid based on the same evidence, why do we believe one over the other? This is a direct challenge to the inductive inference that is at the heart of scientific reasoning. It forces us to confront the fact that our scientific theories are not always as certain as we like to believe. The paradox also introduces the idea of projectable predicates, or concepts that are reasonable to use for making predictions about the future. According to Goodman, green is a projectable predicate, because it reliably predicts that future emeralds will be green. However, Grue is a non-projectable predicate, meaning that it doesn't have the same predictive power for future observations. This concept cuts to the heart of how we differentiate between terms that seem to fit our observations but are not useful for making future predictions. The Grue and Bleen paradox, in a sense, illustrates the limitations of our inductive reasoning, and raises profound questions about how we define the categories we use to understand the world. It shows us that even simple concepts, like color, are not as straightforward as we might think. When we take a closer look at the process by which we make predictions based on past experiences, it becomes clear that certainty is often more about convention than about the solid logic we rely on to justify our beliefs. Ultimately, the paradox serves as a reminder that the language we use to describe the world is not always as neutral or objective as we assume. Our definitions, our categories, and even our understanding of the future are shaped by the choices we make when constructing our theories. The Grue and Bleen paradox invites us to rethink how we approach generalization, prediction and logic in a world that is far more nuanced and uncertain than we might have imagined. By questioning the assumptions behind the terms we use, Goodman's paradox reveals that even the simplest acts of reasoning, like predicting that an emerald will be green, are more fraught with philosophical implications than they first appear. It forces us to dig deeper into the nature of inductive reasoning, and reminds us that sometimes, the most seemingly trivial distinctions can lead to profound puzzles that challenge the very way we think about knowledge and the world around us. Arrow's impossibility. Theorem is one of the most profound and surprising results in social choice theory and economics. Developed by the American economist Kenneth Arrow in 1951, this theorem explores the seemingly impossible task of finding a voting system that consistently reflects the collective preferences of individuals, while satisfying a set of basic, reasonable conditions. At first glance, it might seem like we're talking about an issue of everyday voting, like how to fairly elect a president or choose the best restaurant for dinner. But the theorem reveals a deep flaw in our understanding of collective decision-making, one that challenges our intuitions about fairness and democracy. The setup of Arrow's theorem involves a society of individuals, each with their own preferences about a set of alternatives. Say a group of people choosing between different political candidates or policies. The goal is to aggregate these individual preferences into a single collective decision that reflects the will of the group. To make sure that the process is fair and reasonable, Arrow outlined a set of conditions that any voting system should meet. 1. Unrestricted domain. Every individual's preferences should be allowed, meaning the system must be flexible enough to accommodate any possible set of individual rankings of the alternatives. 2. Non-dictatorship. No single individual should be allowed to dictate the outcome of the election. The preferences of one person should not override the collective will of the group. 3. Pareto efficiency. If every individual prefers one alternative over another, the collective choice should reflect that preference. In other words, if everyone agrees on an option, it should win. 4. Independence of irrelevant alternatives. The ranking of two alternatives should not be affected by the presence or absence of other alternatives. In other words, adding a new choice shouldn't change the relative ranking of the original options. Arrow's theorem states that no voting system can satisfy all of these conditions simultaneously. Under certain basic assumptions, it's as if we've been handed a list of reasonable requirements for a voting system, only to find that no system can satisfy all of them without violating at least one condition. The theorem shows that there is no perfect way to aggregate individual preferences into a group decision that meets all of the fairness criteria. This result is striking because it suggests that even with the most thoughtful, rational, and democratic frameworks, we're always going to face some compromise when it comes to collective decision-making. At the heart of Arrow's impossibility lies the idea that group preferences are inherently messy and cannot be easily distilled into a consistent, fair, and reliable system. When you try to combine the individual rankings of alternatives, there are inherent contradictions that arise, just like trying to merge two different perspectives without losing some nuance. The theorem proves that any voting system will inevitably fail to meet at least one of the basic fairness conditions, leaving us with a paradox. The more we try to refine our decision-making process, the more we seem to undermine its fairness. What makes Arrow's theorem so powerful is that it applies to any voting system, no matter how complex or carefully designed. Whether we're dealing with a simple majority vote, a ranked choice system, or something more intricate like the board account, the impossibility still holds. This means that no matter what kind of voting system we adopt, we're always going to face some form of injustice or inefficiency. There is no perfect democratic process. The best we can hope for is to choose a system that minimizes the flaws, rather than eliminating them entirely. This result has profound implications for the design of democratic institutions and electoral systems. It shows that fairness in voting is not just a matter of creating rules that everyone can agree on. It's also about understanding that any system will have trade-offs. In fact, the theorem raises important questions about what it means for a system to be fair. Does fairness mean that every individual has an equal voice? Or does it mean that the collective decision represents the greatest good for the greatest number? What if a system fails to meet the conditions of fairness, but still leads to generally acceptable outcomes? Arrow's theorem doesn't provide answers to these questions, but it certainly makes us rethink how we view the relationship between individual choice and collective decision-making. It's also worth noting that Arrow's theorem has deep philosophical implications. It touches on fundamental questions about collective judgment, individual rights, and how we navigate the complexities of human preferences. In a sense, it shows us the inherent limitations of our idealistic notions of democracy and collective action. We are forced to accept that there's no perfect system that can perfectly balance fairness, efficiency, and individual autonomy. This revelation invites us to approach decisions with a greater sense of humility, acknowledging that every system has its weaknesses, and that perfection is not achievable in human society. In modern applications, Arrow's theorem is often used as a benchmark in the study of social choice theory, economics, and political science, where it continues to shape discussions about how to design systems that are as fair and representative as possible. It highlights the tension between idealism and pragmatism, urging us to carefully consider how we define fairness and what compromises we're willing to accept when making collective decisions. Ultimately, Arrow's impossibility theorem stands as a testament to the challenges of collective decision-making and the limitations of our mathematical models for representing human preferences. It invites us to reflect on the complexities of democracy and decision theory, and encourages us to explore ways to mitigate the inherent contradictions in our systems, even if we can never fully eliminate them. Uncomputable numbers are one of the most quietly mind-bending ideas in theoretical mathematics and computer science, revealing that even within the realm of numbers, where logic seems absolute and precision reigns supreme, there exist quantities so complex that no algorithm could ever calculate them completely. To understand uncomputable numbers, it helps to first imagine what it means for a number to be computable. A computable number is any real number for which there exists a finite step-by-step procedure, an algorithm, that can approximate it to any desired level of accuracy. This includes familiar values like pi, or e, irrational but still computable, because we have concrete ways of generating more and more digits as needed. But not all numbers are so cooperative. In fact, most real numbers are not. The set of real numbers is uncountably infinite, while the number of possible algorithms, the number of computer programs, essentially, is countably infinite. That means there are vastly more real numbers than there are algorithms to compute them. Just as there are more points on a line than there are names for those points, there are more numbers than there are ways to calculate them, no matter how clever our machines or how advanced our mathematics becomes. This is where uncomputable numbers live, in that vast silent majority of the real number line that lies beyond the reach of calculation. They cannot be generated by any algorithm, no matter how much time or memory you allow. There's no program, no formula, no clever trick that will give you their digits, even though these numbers are perfectly well defined as real values. They exist, they are real in a mathematical sense, and yet they are fundamentally inaccessible. One of the most famous examples of uncomputability is Chaitin's constant, often denoted as omega. This number represents the probability that a randomly generated computer program will eventually halt. But here's the twist: omega is well defined and has a specific value between 0 and 1, yet its digits encode the solution to the halting problem, an unsolvable problem in computation that Alan Turing proved in the 1930s. The halting problem asks whether a given computer program will eventually stop running or continue forever. Turing showed that there is no general method that can determine the answer in all cases. So since omega encodes this unsolvable problem, it means that omega itself is uncomputable. Even though it has a real fixed value, there is no algorithm that can list out its digits, because doing so would be equivalent to solving the halting problem, which we know is impossible. This concept shakes up our understanding of what it means to know a number. We're used to thinking of numbers as things we can express, write down, or compute. But uncomputable numbers remind us that existence in mathematics does not require accessibility. They exist in a kind of mathematical fog, perfectly real and yet forever out of reach. What's even more fascinating is that these numbers aren't rare, they're the norm. The set of computable numbers, though infinite, is tiny compared to the vastness of the real numbers. If you were to randomly pick a real number between 0 and 1, the probability that it would be computable is exactly 0. That means uncomputable numbers are not fringe cases, they're almost everything. We live in a world where most numbers are so rich in complexity that no amount of computational effort could ever fully uncover them. This realization has deep implications for mathematics, computer science, and even philosophy. It highlights the limits of formal systems and shows us that there are truths which are real but not knowable in the usual way. No matter how powerful our machines become, or how advanced our algorithms grow, some parts of mathematical reality will remain fundamentally unknowable, not because we haven't discovered the right method, but because no method exists. It invites a kind of humility in the face of infinite complexity, reminding us that not all things that exist can be expressed. Uncomputable numbers also intersect with questions about randomness and information. Many of these numbers are in a sense algorithmically random. Their digits display no discernible pattern and contain no compressible structure. To describe them would require more information than any finite description can hold. They are the mathematical equivalent of pure noise, and yet they are real, legitimate numbers, each sitting quietly on the number line, unknowable yet unshakably there. In a way, uncomputable numbers are like the dark matter of mathematics, making up the vast majority of the landscape, invisible to direct exploration, yet undeniably a part of the structure. They show us that while we may be able to build bridges with numbers, fly rockets using equations, and model the universe with precision, there will always be more beyond our reach, hidden realms where logic still holds, but our tools cannot follow. The mathematics behind optical illusions reveals a surprising and beautiful truth about the way our minds interpret the world through the language of geometry, proportion, symmetry, and spatial reasoning. At first glance, optical illusions might seem like mere tricks of the eye, clever images that fool us into seeing movement where there is none, shapes that shift depending on how we look at them, or colors that seem to change just by being placed next to one another. But beneath these visual effects lies a deep connection to mathematical principles, particularly in the fields of geometry, topology, and even calculus. What makes optical illusions so fascinating is that they expose the subtle difference between what is there and what we perceive, and mathematics provides the structure that helps us understand why. Take, for example, the Müller-Lyer illusion, where two lines of the same length appear drastically different, simply because of the direction of small arrowheads placed at the ends. This illusion reveals how our brain interprets depth and perspective based on contextual cues. It's not that the line actually changes, it's that our brain applies geometric rules from our experience of the physical world, like linear perspective and foreshortening, to interpret the image in 3 dimensions even though it's a flat drawing. In mathematical terms, the illusion exploits projective geometry, the same framework used to create realistic drawings of 3D objects on 2D surfaces. The trick isn't in the lines themselves, but in the mathematical assumptions the brain makes about how space is organized. Another striking example is the Ames room, a distorted room that looks normal when viewed from a specific angle, but causes people inside it to appear to grow or shrink dramatically as they walk from one side to the other. The illusion works because the room is built using precise geometric distortions that are carefully calculated to preserve visual cues of a rectangular space. Behind the scenes, it's all about perspective projection and the transformation of space in 3 dimensions, concepts that are foundational in mathematical modeling and computer graphics. The illusion only works because our brain assumes that walls are straight, ceilings are level, and floors are flat, assumptions grounded in Euclidean geometry that the illusion manipulates with exact mathematical precision. Some illusions rely on patterns and repetition to create visual effects that seem dynamic or unstable, like the cafe wall illusion, where parallel lines appear to be sloped due to the staggered placement of black and white tiles. This illusion ties directly into the mathematics of spatial frequency, which describes how patterns repeat over space, and how our visual system processes them. It's related to the same ideas that underpin Fourier analysis, a mathematical method used to break down complex signals into simple waves. Our eyes are constantly filtering visual information in much the same way, and illusions like these occur when certain spatial patterns overload or trick those filters. Then there are impossible objects, figures like the Penrose triangle, or the impossible staircase, which appear logical at a glance but fall apart under scrutiny. These illusions challenge the very notion of physical coherence, and rely on subtle violations of geometric rules that only become apparent when you trace the figure more carefully. They are examples of how topology, the mathematical study of space and continuity, can be pushed to create objects that defy construction in the real world. The shapes feel wrong, but they're not nonsensical. They are made using perfectly logical steps that exploit the limitations of human depth perception, and our tendency to prioritize local visual consistency over global coherence. In many optical illusions, symmetry and asymmetry play key roles in how we perceive balance and distortion. Symmetry is a deeply mathematical concept. It involves invariance under transformations like reflection, rotation, or translation. When symmetry is subtly broken, our brain often compensates for the difference in unexpected ways, leading to illusions of movement, tension, or imbalance. Artists and architects have used this understanding for centuries, employing techniques grounded in group theory and transformational geometry to control how viewers experience their work. What all of these illusions demonstrate is that vision is not passive. It is an active, inference-driven process shaped by mathematical rules that our brain applies unconsciously. We're constantly using models of geometry, proportion, and probability to make sense of what we see, and most of the time these models work well. But illusions reveal the hidden scaffolding of perception by pushing those models to their limits. They show us that seeing is not believing, seeing is calculating, and sometimes those calculations lead us astray. This interplay between perception and mathematics is not just theoretical. It's foundational in fields like computer vision, where algorithms must replicate or interpret human visual processes, and in neuroscience, where mathematical models help describe how the brain encodes spatial relationships and motion. It also plays a role in design, architecture, animation, and even medical imaging, where illusions must be carefully avoided or sometimes intentionally used to guide attention. So when we encounter an optical illusion, we're not just being fooled, we're being offered a glimpse into the incredible machinery of our own perception, shaped by centuries of mathematical structure. The illusions work not because they break the rules of reality, but because they so precisely obey the rules of how we think reality is constructed. And in doing so, they give us a unique window into the hidden geometry of thought itself. The Klein Paradox is one of those strange and beautiful constructions in mathematics that invites us to rethink our understanding of space, boundaries, and dimensionality, by presenting an object that seems to defy the very concept of inside and outside. At first glance, the Klein bottle looks like a kind of twisted glass sculpture, a tube that curves around and feeds into itself in a way that's hard to follow with the eye. But what makes it so fascinating isn't just its appearance, it's that it's a shape with no edges, no holes, and most peculiarly, no distinct inside or outside. It is what mathematicians call a non-orientable surface, meaning that if you travel along its surface, you can return to your starting point flipped, as though left and right have been swapped along the way. The paradox of the Klein bottle begins with its construction. It's usually described as being formed by taking a cylinder, curving it around so the ends meet, and then somehow passing one end through the side of the cylinder to attach it back to itself, but without creating a seam or boundary. In three-dimensional space, this process seems to require the surface to intersect itself, almost like cheating. That's because the Klein bottle can't truly exist in 3 dimensions without this intersection. It's a 4-dimensional object being projected into a lower dimensional space, like trying to draw a 3-dimensional cube on a flat piece of paper. The paradox arises from this mismatch between the abstract purity of the mathematical concept and the physical limitations of the space we live in. In a way, the Klein bottle is a natural extension of the Mobius strip, which is another non-orientable surface. The Mobius strip is created by taking a strip of paper, giving it a half twist, and joining the ends together. It has only one side and one boundary, which already feels a bit like a magic trick. But the Klein bottle takes that further, eliminating the boundary altogether, and creating a surface that's continuous, closed, and yet has only one side. If you imagine a tiny ant crawling along the surface of a Klein bottle, it would be able to explore the entire object without ever crossing an edge or encountering a border, and without ever stepping off the surface, because there is no off. It's a surface that contains itself, looping around in a way that challenges our usual spatial intuitions. The mathematics behind the Klein bottle is rooted in topology, the branch of mathematics concerned with the properties of space that remain constant under continuous deformation. Stretching, bending, twisting, but not tearing or gluing. In topology, shapes are classified not by their angles or lengths, but by their fundamental structure, how many holes they have, how they can be connected, and how surfaces behave. The Klein bottle is part of a family of surfaces that include spheres, tori, and Mobius strips, but it stands out because of its non-orientability and boundarylessness. What's particularly interesting is how the Klein bottle forces us to reconsider what it means for a surface to be real. We can build physical models of Klein bottles, glass sculptures, wireframes, 3D prints, but these are always imperfect because they require the surface to pass through itself, something that doesn't happen in the pure mathematical version. The true Klein bottle lives in four-dimensional space, where it can be constructed without self-intersection. In that space, it becomes a smooth and perfectly coherent object, free from the limitations that three-dimensional space imposes. And yet, even though we can't truly perceive four dimensions, mathematics allows us to reason about them, to define objects that exist beyond our senses and explore their properties with precision. The Klein bottle paradox doesn't break the rules, it redefines them. It shows us that our everyday experience of space is just one version of what space can be, and that by stepping into abstraction, we can uncover shapes and structures that seem impossible but are mathematically consistent, and even elegant. It also hints at deeper connections to physics and cosmology, where higher dimensions and non-orientable spaces have been considered in theories about the shape of the universe and the fabric of space-time itself. So when we look at a Klein bottle, not just as a quirky object, but as a window into higher dimensional thinking, we're reminded that space isn't always what it seems. Surfaces can loop back on themselves, boundaries can disappear, and distinctions like inside and outside can dissolve into a single seamless whole. It's a shape that exists not to be built, but to be understood, and in that understanding, it invites us to stretch our minds just a little beyond the familiar edges of geometry. The black hole information paradox is one of the most intriguing and unresolved puzzles at the intersection of physics, mathematics, and philosophy. A conflict between the smooth geometry of general relativity and the probabilistic laws of quantum mechanics that reveals just how far we are from fully understanding the universe at its most extreme edges. At its core, this paradox asks a deceptively simple question: what happens to information when it falls into a black hole? But the implications of the answer touch on the very foundations of reality, and challenge our assumptions about time, entropy, and the fundamental consistency of physical laws. Black holes are regions of space where gravity is so intense that nothing, not even light, can escape once it passes the event horizon, the boundary beyond which the gravitational pull becomes overwhelming. According to general relativity, once something crosses this boundary, all of its properties, its mass, charge, and angular momentum, are preserved in the black hole, but the fine-grained details about its internal state are lost to the outside world. This idea leads to the so-called no-hair theorem, which says that black holes can be completely described by just a few simple quantities, regardless of what they're made of. A black hole formed from a library full of books, a collapsing star, or a cloud of gas will look exactly the same from the outside, if their mass, charge, and spin are identical. But here's where the paradox arises. Quantum mechanics insists that information is never truly destroyed, that if you know the complete state of a system at one point in time, you can in principle determine both its past and its future with perfect accuracy. This principle, known as unitarity, is baked into the mathematics of quantum theory, and it's one of the reasons why probabilities in quantum mechanics always add up to 1. So if you throw a book into a fire, the book is destroyed, but the information about the book's arrangement, its ink patterns, its molecular composition, is not lost, just scrambled and dispersed into heat and smoke. In principle, it's still there, hidden in the complexity of the particle's motion. But if you throw that same book into a black hole, things get more complicated. In the 1970s, Stephen Hawking showed that black holes are not entirely black. They emit radiation due to quantum effects near the event horizon, a phenomenon now called Hawking radiation. This radiation appears completely random, uncorrelated with whatever fell in, and over time, it causes the black hole to shrink and eventually evaporate entirely. If this radiation carries no information about what went into the black hole, and if the black hole disappears completely, then the information seems to be lost forever, violating the principles of quantum mechanics. And that is the black hole information paradox. General relativity says it's gone. Quantum theory says it can't be. The mathematics of this paradox leads to some deep and often unsettling implications. If information can be destroyed, then quantum mechanics might need to be revised in ways we don't yet understand. On the other hand, if information is somehow preserved, it must be encoded in the Hawking radiation itself, in a way so subtle that it escapes our current tools of analysis. This leads to questions about entanglement, entropy, and the geometry of space-time itself, ideas that have become central to modern efforts to reconcile quantum theory with gravity. One proposed resolution is the concept of black hole complementarity, which suggests that information is both reflected at the event horizon and absorbed into the black hole, depending on the observer's frame of reference, but never accessible in both ways at once. Another dramatic idea is the holographic principle, which proposes that all the information within a volume of space can be described by data encoded on its boundary, like a hologram. In this view, the event horizon might act as a kind of cosmic memory storage, preserving the information in a two-dimensional form that can eventually leak back out through Hawking radiation. More recently, researchers have explored the idea of firewalls, hypothesized boundaries of intense energy at the event horizon that could disrupt our expectations about smooth space and force us to revise either relativity, quantum mechanics, or both. Despite decades of study, there is still no universally accepted solution, and that's part of what makes the black hole information paradox so compelling. It sits at the crossroads of two incredibly successful but incompatible theories, highlighting a deep fracture in our understanding of nature. The paradox doesn't just point out a missing piece, it suggests that the puzzle itself might need to be reimagined. Ultimately, the black hole information paradox reminds us that even in the most silent, remote corners of the cosmos, the universe is still governed by rules we are only beginning to grasp. It challenges our belief in permanence, in determinism, and in the idea that knowledge, once acquired, can never truly vanish. In the quiet collapse of a dying star, in the radiation that slowly trickles into space, and in the equations that try to tie it all together, we see a mystery not just about black holes, but about the nature of knowledge itself. The pigeonhole principle is one of those deceptively simple ideas in mathematics that hides a surprising depth beneath its almost obvious surface. At first glance, it sounds more like common sense than a profound mathematical insight. But the more closely you look, the more you realize how this humble principle shows up in unexpected places, revealing certainty in situations that might otherwise seem chaotic or random. In its most basic form, the principle says that if you have more pigeons than pigeonholes, and you try to put each pigeon into a hole, then at least one hole must contain more than one pigeon. It's such an intuitive idea that it almost doesn't seem worth stating, and yet it forms the backbone of many powerful arguments in combinatorics, probability, computer science, and beyond. What makes the pigeonhole principle so fascinating is that it guarantees the existence of something without necessarily telling you exactly where to find it. It's a form of existence proof, a way of saying that certain outcomes are not just possible but inevitable, based purely on counting and logic. For instance, imagine you have 13 people in a room. Since there are only 12 months in a year, the pigeonhole principle tells us that at least 2 people must share a birthday month. It doesn't matter who they are or when they were born. The conclusion follows unavoidably from the numbers alone. That's the quiet power of the principle. It lets you make confident conclusions in the absence of specific details. In mathematics, this idea becomes a tool for proof by contradiction, where you assume the opposite of what you want to prove and use the pigeonhole principle to show that such an assumption would lead to an impossibility. This method has been used to prove results ranging from the existence of repeated patterns in number sequences to the impossibility of designing certain kinds of error-free communication systems. In computer science, it helps explain limits on data compression. For example, if you try to compress every file into a smaller size, eventually you run out of shorter files to assign, and some files must end up sharing the same compressed version. That overlap creates ambiguity, meaning perfect universal compression is impossible. Once again, the pigeonhole principle steps in to reveal an unavoidable truth. But it's not just about numbers or files. The principle also applies to the physical world in subtle ways. If you have a group of people and a limited number of available resources, or a set of physical locations and a fixed number of objects to distribute, the principle helps predict outcomes that are guaranteed by the structure of the problem. It shows up in nature, in games, in scheduling, in hashing algorithms, and in the strange little coincidences of daily life. If you've ever been surprised by how often people share birthdays, or how quickly socks seem to disappear in the laundry, you've experienced the pigeonhole principle in action. whether you realized it or not. There's also something beautifully paradoxical about how this principle takes the ordinary and makes it profound. It doesn't require advanced machinery or abstract symbols, just a clear statement about quantities and locations, and yet from that simplicity it gives rise to truths that might otherwise be hidden from view. It reveals the patterns that must exist when we try to cram too much into too little, and it reminds us that mathematics isn't always about finding exact answers. Sometimes, it's about knowing that certain answers must exist. So even though it sounds like something a child might say, that if there are more things than places to put them, then something has to share, the pigeonhole principle remains a cornerstone of logical reasoning. It whispers to us that structure underlies even the messiest situations, and that sometimes, inevitability is a more powerful idea than precision. In its own quiet, understated way, this principle captures the essence of mathematical thinking, not by dazzling us with complexity, but by revealing the deep certainty hidden in simplicity. Cantor's diagonal argument is one of the most elegant and mind-expanding results in the history of mathematics. A quiet but revolutionary proof that not all infinities are created equal. Introduced by the German mathematician Georg Cantor in the late 19th century, this argument fundamentally changed the way we think about the infinite, by showing that some infinite sets are so vast, so uncontainable, that they can't be matched up one-to-one with even other infinite sets. It's a paradox of size within the very idea of infinity itself, and its proof relies on nothing more than careful logic, and a simple, almost playful insight. To understand it, first imagine the set of all natural numbers, 1, 2, 3, and so on, stretching out endlessly. This is an infinite set, and it seems pretty big. But now think about the set of real numbers between 0 and 1. All the decimals like 0.1, 0.123, 0.999, and so on, going on forever without repeating in most cases. Intuitively, it might feel like you could list all of these numbers, assigning one to each natural number in a long, neat sequence. But Cantor showed that no matter how cleverly you try to list them, no matter how exhaustive your sequence seems, you will always miss some, not just one or two, but an uncountable infinity of them. And he proved this in a beautifully clever way using what's now called the diagonal argument. Imagine you've written down a list of decimal numbers, each meant to represent one of the real numbers between 0 and 1. Each number in the list goes on forever after the decimal point, like 0.1234556, 0.987654, and so on. Cantor's insight was to construct a new number that differs from each number on the list in at least one digit. He does this by taking the first digit from the first number, the second digit from the second number, the third digit from the third number, and so on, forming a diagonal through the list. Then for each digit on this diagonal, he changes it, maybe by adding 1 to it or switching it to something else, to make a new digit that's different from what's in that position. The resulting number will differ from the first number in the first digit, the second number in the second digit, and so on, which means this new number cannot be anywhere on the list, because it differs from every number at least somewhere. And just like that, Cantor proved that no list, no matter how infinite, can capture all the real numbers between 0 and 1. The set of natural numbers is countably infinite. You can line them up in a sequence, but the real numbers are uncountably infinite, a larger kind of infinity that defies enumeration. This revelation was both thrilling and unsettling to mathematicians at the time, because it showed that even in the realm of the infinite, there are hierarchies. Some infinities are strictly bigger than others. This idea forms the foundation of set theory, the branch of mathematics that studies collections of objects, and it opened the door to a completely new understanding of mathematical structure. It also introduced the concept of cardinality, a way of measuring the size of infinite sets. The natural numbers have a cardinality called Crawford Aleph null, while the real numbers have a greater cardinality. Cantor even asked whether there was an intermediate size between these two infinities, a question known as the continuum hypothesis, which remains one of the most famous problems in mathematical logic. What's so beautiful about the diagonal argument is how gentle and precise it is. There's no need for complicated equations or heavy machinery, just a quiet logic that reveals something profound and strange about the infinite. It teaches us that even in a space as seemingly boundless as the real number line, there are patterns and limits to what can be known or named. And it shows how mathematics can use simple tools, a list, a diagonal, a bit of imagination, to uncover truths that are far bigger than they first appear. Cantor's diagonal argument doesn't just tell us that some infinities are bigger, it invites us to rethink what infinity means, how it behaves, and how much more there might be beyond what we can ever hope to list or count. It's a soft but powerful reminder that even in the infinite, there is structure, and even in structure there is wonder. The arrow of time paradox is one of those quietly profound puzzles that sits right at the intersection of physics, mathematics, and philosophy, gently asking why time seems to flow in only one direction, even though the fundamental laws that govern the universe don't appear to prefer one direction over the other. It's something we all experience intuitively. We remember the past but not the future. We see eggs break but never spontaneously reassemble, and we grow older rather than younger. This sense of time moving forward from what was to what will be feels so natural that we rarely stop to question it. But when we do, we find that the universe's underlying rules offer no obvious reason for this forward motion. Mathematically, most of the equations in classical physics and quantum mechanics are time-symmetric, meaning that if you ran the clock backward, those same equations would still hold. Newton's laws, for instance, don't care if time flows forward or backward. If you filmed 2 billiard balls colliding and then played the video in reverse, the motion would still make perfect physical sense. But in reality, we only ever see time unfolding in one direction, toward increasing disorder. This leads us to entropy, the key idea in thermodynamics that helps explain the arrow of time. Entropy is a measure of how disordered or spread out a system is. According to the second law of thermodynamics, in an isolated system, entropy tends to increase over time. This means that things naturally move from states of order to states of disorder, like a tidy room becoming messy, or heat spreading from a hot object to a cold one until equilibrium is reached. This gradual increase of entropy gives time its apparent direction, because we can distinguish the past when things were more ordered from the future, when things will be more random. But this raises a deeper question: if the laws of physics are symmetric, why does entropy increase at all? This is where the paradox truly begins. If the universe's laws don't care which way time goes, then why did the universe start in such a low entropy, highly ordered state in the first place? Why wasn't it already in a state of maximum entropy, complete randomness, where no arrow of time would emerge at all? The arrow of time seems to require special initial conditions, but those conditions themselves feel improbable. And so the paradox lingers. The laws are reversible, but our experience of time isn't. We live in a world where broken cups don't unbreak and memories live only in one direction, even though the equations suggest they could go either way. Some theories try to resolve the paradox by looking to cosmology, suggesting that the Big Bang provided the incredibly low entropy starting point that defines the direction of time for the entire universe. Others speculate about the role of quantum measurement in information, wondering whether the process of observing a system might somehow contribute to the sense of time's flow. And still others consider the possibility that time, as we experience it, might be more of an emergent phenomenon than a fundamental one. Not something built into the fabric of reality, but something that arises from the way complex systems behave. There's something poetic about how the arrow of time connects the smallest scales, atomic particles bumping into each other, with the largest scales of galaxies and the fate of the cosmos. It reminds us that our lived experience, with all its memories and milestones, is part of a broader mathematical story, one that still holds mysteries we haven't fully unraveled. And even though we might not yet have a complete answer to why time moves forward, the search for that answer continues to draw scientists and philosophers alike into deeper explorations of what it means to exist in a world where the past is fixed, the future is uncertain, and the present is always slipping away. The prisoner's dilemma is one of the most quietly profound ideas in mathematics and game theory, a scenario that seems simple on the surface but reveals deep insights about trust, cooperation, and the surprising complexity of rational decision-making. It begins with a story, almost like a thought experiment. Two individuals are arrested and accused of a crime, but the prosecutors don't have enough evidence to convict them without a confession. So each prisoner is offered a choice: betray the other by testifying, or stay silent. If both prisoners stay silent, they each serve only a short sentence. If one testifies while the other remains silent, the one who testifies goes free, and the other receives a much longer sentence. But if both testify, they both get punished, though not as severely as if only one had stayed loyal. The dilemma lies in the fact that, From a purely self-interested perspective, each prisoner has an incentive to betray the other, because no matter what the other person does, testifying always results in a better or equal outcome for the individual. And yet, if both follow that logic, they end up worse off than if they had both remained silent and cooperated. This paradox cuts to the heart of human behavior, because it shows how rational decision-making can sometimes lead to irrational outcomes when individuals act purely in their own interest without considering the effect on the group. It's not just a quirk of hypothetical prisoners. Versions of this dilemma show up all over real life, from economics and politics to relationships and international strategy. Companies might undercut each other in a pricing war even though mutual restraint would be more profitable. Countries might stockpile weapons out of fear, even when mutual disarmament would make everyone safer. People might act selfishly in shared environments, depleting resources even though cooperation would preserve them for all. Mathematically, the prisoner's dilemma is framed in terms of payoff matrices, where each player's outcome depends not only on their own decision, but on the decision of the other. And what makes it particularly fascinating is how it challenges the classic idea of rationality. The dominant strategy, the one that seems best no matter what, leads both players to a suboptimal outcome. It's a reminder that in a connected world, doing what's best for oneself in isolation may not actually be best at all. When the game is repeated over time, a version known as the iterated prisoner's dilemma, things get even more interesting. Patterns emerge, strategies like tit for tat, where players begin by cooperating and then mirror their opponent's previous move, tend to perform surprisingly well. These kinds of interactions show that trust, reputation, and forgiveness can become mathematically viable strategies, even in a competitive environment. It suggests that cooperation isn't just an idealistic hope, but something that can evolve naturally when individuals recognize the value of long-term interaction over short-term gain. The beauty of the prisoner's dilemma lies in its clarity and in how it gently exposes the tension between selfishness and collaboration, between logic and empathy. It asks us to consider how much we're willing to trust others, how we weigh risk and reward, and whether we can truly achieve better outcomes when we choose to cooperate, even when it feels safer not to. It reminds us that mathematics isn't just about numbers and equations, it's also a language for understanding human choices, the invisible strategies behind our actions, and the subtle dance between competition and connection that shapes the world around us. The four-color theorem is one of those quietly surprising results in mathematics that starts with something so simple and intuitive, coloring maps, but reveals deep insights into the nature of problem solving and the power of modern mathematics. The problem is deceptively straightforward. How many colors do you need to color any map, such that no two adjacent regions share the same color? At first glance, it seems like the answer should be obvious. Surely, it takes just a handful of colors to ensure no two neighboring regions are the same color. But as you start considering more complex maps, it becomes clear that figuring out the minimum number of colors isn't quite as simple as it seems. The four-color theorem, which was first conjectured in 1852 by the British mathematician Francis Guthrie, states that no more than 4 colors are needed to color any map in such a way that adjacent regions are always distinct in color. This sounds easy enough, but proving it took over a century. The four-color conjecture remained unsolved for a long time, despite many attempts by mathematicians to prove or disprove it. It wasn't until 1976 that it was finally proven, and the proof itself was groundbreaking, because it was the first major theorem in mathematics to be proven with the assistance of a computer. The proof involved breaking down thousands of cases and checking them individually using computational methods, a process that was simply beyond the capabilities of human calculation. This new approach to mathematics, combining human insight with computational power, opened up an entirely new chapter in mathematical problem solving, raising questions about the role of computers in proofs and the limits of human intuition. The four-color theorem also holds a deep mathematical beauty in how it links simple geometry with complex combinatorics. At its core, the problem is about graph theory, where regions on a map are considered as vertices in a graph, and edges represent borders between adjacent regions. The theorem suggests that no matter how complex the map, whether it's a simple country or a sprawling, intricately divided land, you can always color it using at most 4 colors so that no two adjacent regions share the same one. It's a subtle reminder that even in seemingly ordinary situations, there's often hidden complexity waiting to be uncovered. The theorem also brings us face to face with the limitations of our own reasoning. We might think at first that 4 colors are far too many. Surely we could do it with 2 or 3. And yet, the theorem shows us that the number of colors required isn't based on any intuition we might have from looking at small maps, but rather on a deep and underlying structure that holds true for all possible maps, no matter how large or intricate. It's a reflection of how mathematics can reveal universal truths that are beyond the reach of simple observation. What makes the 4-color theorem particularly compelling is that, like many great results in mathematics, it's a perfect balance of simplicity and depth. The question itself is easily understandable, even by a child, yet the journey to proving it stretches the limits of human thought and computational power. It shows us that problems we think we understand, things we take for granted, like coloring regions on a map, often have much more to them than we initially realize. It's also a reminder of the evolving nature of mathematical exploration. What began as a simple curiosity about maps led to a proof that incorporated elements of computation, graph theory, and logic, changing the landscape of mathematics forever. In a way, the 4-color theorem doesn't just offer an answer to a specific problem. It invites us to reconsider how we approach problems themselves, whether in mathematics or in life. The unexpected, the complicated, and the profoundly simple are often intertwined, and sometimes, the solutions to the most basic questions are the hardest to find. Benford's law is one of those curious and almost magical phenomena that feels like it shouldn't be true, yet it holds up time and time again. At first glance, it seems utterly counterintuitive. The law suggests that in many sets of real-world data, the leading digits are not uniformly distributed. Instead, smaller digits, especially the number 1, appear disproportionately often as the first digit, with the frequency of each successive digit decreasing as you move up the scale. In other words, the number 1 is more likely to appear as the first digit than the number 9. And this pattern continues across a wide variety of datasets, from financial records to populations, from lengths of rivers to physical constants. The fascinating thing about Benford's law is that it's not tied to any particular scale or unit of measurement. Whether you're looking at the size of cities, the lengths of mountains, or even the results of scientific experiments, the distribution of first digits tends to follow the same surprising pattern. In many cases, the number 1 shows up about 30% of the time as the first digit, while the number 9 appears as the first digit only about 5% of the time. This phenomenon is called digit bias, and it can be found in all sorts of places you wouldn't expect, from the most mundane datasets to the most complex ones. But why does this happen? The explanation lies in the logarithmic nature of numbers. When numbers span several orders of magnitude, for example, if you're comparing the heights of mountains, or populations of countries, or the financial figures of companies, the chance of smaller numbers appearing as the first digit is higher because of the way numbers scale. Numbers like 1, 2, and 3 have more room to appear at the beginning of larger numbers. For example, there's a greater chance that a number like 123,000 is chosen randomly than something like 900,000, because it takes fewer steps to get to 123 from 1 than it does from 9. Benford's law has found surprising applications beyond mere curiosity. It has been used in the detection of fraud, for instance. When people manipulate numbers, as in financial statements or tax returns, the resulting data often doesn't follow the natural distribution predicted by Benford's law. This anomaly can serve as a red flag, signaling that the data might not be as legitimate as it appears. It also plays a role in forensic accounting, helping auditors spot irregularities and uncover fraudulent activities. It's not just limited to numbers, either. Benford's law has been observed in a wide variety of unexpected places, such as scientific data, the size of earthquakes, the frequency of words in large bodies of text, and even the distribution of prime numbers. Wherever there's data that spans several orders of magnitude, chances are good that Benford's law will apply. There's something almost elegant in the simplicity of Benford's law. It reveals the subtle and often unnoticed patterns in the world around us. It shows us that even in the chaos of seemingly random numbers, there's a hidden order waiting to be discovered. And while the law itself doesn't offer a deeper understanding of the why behind the numbers, it serves as a reminder that there are always layers to reality that we may overlook, and sometimes, patterns emerge in the most unexpected ways. Benford's law is a quiet reflection of the underlying order of nature, suggesting that the world is more predictable than we might think, even when we're looking at data that seems entirely random or haphazard at first. It invites us to look more closely at the numbers that surround us, and to consider how deeply embedded mathematical truths can be, even in the most everyday situations. The Collatz Conjecture is one of those deceptively simple problems that has fascinated mathematicians for decades, captivating minds with its apparent simplicity and baffling complexity. It's often called the 3n+1 problem. But don't let the name fool you. The simplicity of its definition masks the deep mystery at its core. The conjecture begins with any positive integer. If the number is even, you divide it by 2. If it's odd, you multiply it by 3 and add 1. You then repeat this process with the new number, continuing indefinitely. The Collatz conjecture suggests that, no matter which positive integer you start with, the sequence of numbers you generate will always eventually reach the number 1. At first glance, this might seem like a trivial task. You might think, well, the numbers must eventually fall into some pattern. But despite the simplicity of the rules, no one has ever been able to prove this conjecture for all numbers. Mathematicians have tested it on an enormous range of integers, and in every case, the sequence eventually does fall to 1. Yet, despite this empirical evidence, no one has been able to prove that it always works, and no counterexample has ever been found. The mystery remains. What makes the Collatz conjecture so perplexing is that, while it seems like it should be simple to prove, it defies our usual tools for analysis. Unlike other number-theoretic problems, such as prime number theory or even problems involving complex functions, the Collatz problem resists being neatly captured by any existing mathematical frameworks. This has led some mathematicians to consider it a potential example of a problem that is simple to understand but incredibly difficult, or perhaps even impossible to solve. Part of the allure of the Collatz conjecture is its combination of apparent randomness and underlying structure. When you start with a number and begin following the rules, the sequence can behave in a seemingly erratic way. Some numbers seem to jump up dramatically, while others descend in a slow, steady pattern. But no matter how strange the path may seem, all roads seem to lead to 1. This strange mixture of chaos and order sparks curiosity and challenges our intuitions about mathematical problems. What's particularly intriguing is that the conjecture doesn't have a simple solution in the traditional sense. It's not about finding a formula or equation that works in all cases. Instead, it's about understanding a process, about the interplay between even and odd numbers, and how such a simple set of rules can create complexity. The fact that a solution eludes us, despite extensive computational testing, only deepens the mystery. The Collatz conjecture also speaks to something much broader in mathematics, the idea that patterns can exist even in systems that appear random or chaotic. It's a reminder that sometimes the most straightforward-looking problems can hide profound and unexpected depths, and that even seemingly simple sequences can grow into incredibly complex and elusive phenomena. As it stands, the Collatz conjecture is a perfect example of how mathematical exploration doesn't always lead to tidy, predictable answers. Even though we've observed its behavior in billions of cases, the question remains, does it hold for every integer? This open question, which has yet to be resolved, is one of the many unsolved mysteries that continue to challenge and inspire mathematicians today. It encourages us to keep searching for patterns in the world around us, to embrace the beauty of unanswered questions, and to marvel at the strange and unpredictable paths that simple rules can create. Perhaps the most fascinating thing about the Collatz conjecture is the humility it invites. We're reminded that, in mathematics as in life, there are still mysteries to explore, things that may seem simple but resist full understanding. And sometimes, the pursuit of understanding itself can be just as rewarding as finding the answer. Mathematical synesthesia is a truly fascinating and deeply personal phenomenon, where two seemingly unrelated senses, in this case mathematics and perception, become intertwined in the mind. Synesthesia itself is a neurological condition where stimulation of one sensory pathway leads to involuntary experiences in another. For example, some people might see colors when they hear music, or taste flavors when they see certain words. But when it comes to mathematical synesthesia, It's as though mathematical concepts and structures are experienced in ways beyond just the abstract or logical. In this particular form of synesthesia, people often see numbers, equations, or even entire mathematical structures in vivid sensory ways. For some, numbers may have specific colors or textures, or perhaps certain operations like addition or multiplication might evoke physical sensations, sounds, or even tastes. These associations are deeply personal and can vary greatly from one individual to another. To someone with mathematical synesthesia, an equation might not just be a sequence of symbols, but a rich multi-sensory experience that brings the equation to life in a new and unexpected way. The experience of mathematical synesthesia is not just a matter of perceiving numbers differently, but rather engaging with the very feel of mathematics. Imagine a simple number like 5. For some synesthetes, this might be associated with a specific color, perhaps a soft shade of blue, while others might perceive it as a sharp angular shape. Mathematical operations like addition might feel smooth and flowing, while subtraction could feel like a jagged, cutting sensation. This blending of sensory experiences creates a highly individualized and, at times, almost poetic way of thinking about mathematics. The phenomenon highlights something wonderfully profound, that mathematics, often thought of as an abstract logical language, is also capable of stirring emotion and sensory engagement. It underscores the deeply human aspect of mathematical thought, that math isn't just a sterile, cold process of calculation, but something that for some, can be experienced in a visceral and personal way. For those who experience mathematical synesthesia, the relationship between numbers and the world around them becomes a deeply emotional and sensory connection. It's not just a formula to solve, but an entire universe of textures, colors, and sensations that infuse their thinking and problem-solving. What's especially intriguing about mathematical synesthesia is how it offers a glimpse into the brain's remarkable ability to bridge different cognitive domains. Most people experience mathematics as a logical process, a series of mental steps and abstract concepts. But for those with mathematical synesthesia, these concepts can take on a rich sensory quality that opens up entirely new ways of interacting with numbers. It's a reminder that our experience of the world, including the world of mathematics, is shaped not just by reason but by all the senses that contribute to our understanding of reality. Interestingly, mathematical synesthesia also sheds light on the creativity that is often involved in mathematics. Many mathematicians, including those who don't have synesthesia, report experiencing moments of insight or discovery that feel almost like a sudden burst of color or light, as if the solution is visually or emotionally illuminated in their mind. For those with synesthesia, this is a literal experience. The solution might actually appear as a vivid color or take on a form that makes the abstract problem feel real in a tangible way. It highlights the connection between creativity and mathematics, showing that sometimes the most abstract of concepts can evoke a deeply creative, almost artistic response. For those who don't experience mathematical synesthesia, it may be difficult to fully grasp the depth of the sensory world that such individuals experience. But the beauty of it lies in the fact that math, as an intellectual pursuit, is something that doesn't just live in the realm of cold calculations. For some, it becomes a rich multidimensional experience that transcends the abstract and merges with the sensory, transforming numbers and equations into something far more than just logic. The infinite monkey theorem is one of those ideas that might initially sound playful or absurd, but it touches on some deep and profound concepts in probability theory and the nature of randomness. The theorem posits that if you were to take an infinite number of monkeys, each with a typewriter, and let them type randomly for an infinite amount of time, at least one of them would eventually produce the complete works of Shakespeare, or indeed any specific piece of text you might choose. On the surface, the idea of monkeys typing Shakespeare's Hamlet purely by chance seems almost ridiculous. The thought of a monkey randomly hitting keys, producing coherent sentences, much less entire plays, feels absurd. Yet, within the framework of probability, it makes a surprising kind of sense. If you give the monkeys infinite time and infinite chances, all combinations of letters, words, and sentences must eventually occur, including the works of Shakespeare. The theorem is a vivid illustration of how infinite time or opportunities can lead to unlikely events becoming inevitable. It may seem like an absurd idea, but it's a powerful way of demonstrating how probability works when applied on an infinite scale. After all, in a universe of infinite possibilities, Every possible combination of events, no matter how unlikely, will eventually come to pass. This is what the theorem reveals about the nature of randomness, that with enough time or opportunities, the most improbable events are not just possible but inevitable. However, while the theorem is a theoretical construct, it sheds light on deeper philosophical questions. It raises the idea that the seemingly chaotic or random can eventually give way to order and structure, given enough time. When applied to real-world situations, this notion can be surprising. It suggests that, given enough trials, even the most complex systems or patterns, like the works of literature or even the fundamental laws of nature, could emerge from what seems like pure randomness. In practice, though, the theorem is of course not a practical experiment. The idea of an infinite number of monkeys typing for an infinite amount of time is just a thought experiment, meant to demonstrate the consequences of probability when there are unlimited resources. In the real world, the monkeys wouldn't be able to type out Shakespeare's works by pure chance in any reasonable time frame, and they certainly wouldn't be able to produce meaningful text without structure or guidance. The theorem serves not as a blueprint for reality, but as a reminder of the power and paradox of infinite possibilities. The true value of the infinite monkey theorem lies in how it brings the abstract nature of infinity into sharper focus. Infinity, a concept that's often difficult to grasp, is made concrete by the thought of these monkeys, showing that with endless time and endless possibilities, the improbable will inevitably occur. In a way, it helps us understand the vast scale on which the universe operates, reminding us that in an infinite cosmos, even the most minute or unlikely events have a chance of happening. The infinite monkey theorem also serves as a playful metaphor for creativity and the search for meaning in an unpredictable world. It reminds us that sometimes, even in the most random or chaotic moments, something meaningful may eventually emerge. It's a humbling notion, suggesting that from randomness and disorder, great beauty, knowledge and understanding could eventually arise, if only we had the right circumstances, the right amount of time, and the right set of chances. The Mandelbrot set is one of the most mesmerizing and visually captivating concepts in mathematics. A paradoxical blend of simplicity and infinite complexity. Named after the mathematician Benoit B. Mandelbrot, this set arises from the world of complex numbers. Yet it feels almost like a living, breathing object when viewed through the lens of modern mathematics and computer-generated imagery. At its core, the Mandelbrot set is defined by a simple, iterative process. You begin with a complex number, and through a series of mathematical operations, you check whether this number stays bounded or escapes to infinity. It's a simple rule, almost deceptively so. But when this process is repeated countless times, the resulting shape that emerges is nothing short of extraordinary. A wildly intricate, infinitely detailed boundary that seems to stretch on forever. What's so compelling about the Mandelbrot set isn't just the simplicity of the rule, but the way this rule produces intricate, complex patterns. The set itself consists of points in the complex plane that don't escape to infinity when iterated through the process. All the points that do escape form a beautiful boundary, a jagged, self-similar shape that appears both chaotic and orderly at the same time. The boundary of the Mandelbrot set, when zoomed into infinitely, reveals an astonishing level of detail, with patterns repeating themselves in increasingly smaller scales. It's as though the more you look, the more there is to see. A truly infinite variety of forms, all governed by the same underlying rule. One of the most fascinating aspects of the Mandelbrot set is its connection to the concept of fractal geometry. Fractals are structures that exhibit self-similarity at different scales, meaning that the shape looks similar, no matter how much you zoom in. In the case of the Mandelbrot set, this self-similarity isn't exact, but rather it's approximated. As you zoom in on its boundary, you find smaller copies of the overall shape, a repeating pattern that suggests infinite complexity within a finite structure. This idea of infinite detail within a finite space is both beautiful and unsettling, and it challenges our usual understanding of how patterns and order work in the world around us. The experience of looking at the Mandelbrot set is more than just a mathematical exercise. It's a kind of visual journey into the unknown. The colors and shapes that emerge when you plot the set on a computer are stunning, evoking a sense of wonder and awe as the pattern unfolds in front of you. It's not just mathematics, it's an invitation to explore the edges of the known and the unknown. In a way, it mirrors the process of discovery itself, where each new layer of understanding reveals even more questions and layers beneath it. The implications of the Mandelbrot set extend beyond just pure mathematics. Its beauty has captivated artists, scientists, and philosophers alike, showing how the abstract world of numbers and operations can create something that resonates with our sense of wonder and curiosity. It blurs the line between the logical and the creative, reminding us that there's a kind of art in mathematics, a hidden beauty that lies just beneath the surface, waiting to be revealed. The fact that such complex patterns can emerge from such simple rules challenges our notions of what is possible, and invites us to look deeper into the world around us. Mathematically, the Mandelbrot set serves as a powerful reminder of the limits of our understanding. Even though we can understand the set's underlying rule and structure, there's no simple formula to describe its boundary. It's a boundary that in many ways can never fully be captured or comprehended, a structure that defies complete definition, no matter how many times we zoom in. This sense of never quite reaching the bottom of the rabbit hole is part of what makes the Mandelbrot set so captivating. In the broader context, the Mandelbrot set reveals something profound about the nature of infinity and complexity. It shows that even in the most seemingly simple systems, infinite complexity can emerge. It suggests that the universe, much like the Mandelbrot set, is a vast and intricate system where seemingly simple rules can give rise to an endless variety of patterns and phenomena. The Mandelbrot set, therefore, isn't just a curiosity of mathematics. It's a window into a deeper, richer understanding of the world. It invites us to embrace the complexity that lies beneath the surface, and to appreciate the infinite possibilities that emerge from simple, well-defined rules. Through this lens, the Mandelbrot set becomes not just a mathematical object, but a metaphor for discovery itself, a journey into the unknown, where beauty and mystery await at every turn. The birthday paradox is one of those delightful mathematical surprises that challenges our intuitions about probability. At first glance, it seems like a simple idea. After all, how could the chances of two people sharing the same birthday possibly be high, given that there are 365 days in a year? But when we start to dig into the actual probabilities, we realize that our intuitive understanding of chance might not be quite as sharp as we thought. The paradox revolves around the surprising probability that in a group of just 23 people, there's a better than even chance that at least two people will share a birthday. This might sound counterintuitive at first. After all, there are 365 possible birthdays, so you would think the odds of two people sharing a birthday would be relatively low. But the key here is how probability works when we are talking about groups, not pairs. In a room of 23 people, the problem isn't about the chance that any particular pair of people shares a birthday. Instead, it's about how many possible pairs can be formed within that group. For a group of 23 people, there are 253 different pairs of people that could potentially share a birthday. This large number of pairs dramatically increases the likelihood that at least one pair will share the same day. To illustrate, consider the example where you're the first person in a room. The chance that no one shares your birthday is 364 out of 365. Now, you bring in the second person. The chance that they don't share your birthday is also 364 out of 365. You keep going, adding more people, and the chances start to build up that, at some point, two people will share the same birthday. By the time you reach the 23rd person, the odds are surprisingly high that at least one pair will match. What's so fascinating about the birthday paradox is that it reveals how we often underestimate the power of combinations in probability. Our brains are much more accustomed to thinking about the likelihood of individual events, like flipping a coin or rolling a die. But when multiple independent events are involved, as in the case of multiple people in a room, the probability starts to shift in ways we don't expect. This paradox also highlights something about human nature. Our intuition about chance is often skewed, particularly when dealing with larger groups or more complex situations. We tend to think in terms of individual probabilities, the odds of one person sharing a birthday with another. But when we multiply these chances across a whole group, the results become much more surprising. The paradox is a beautiful reminder that probability doesn't always align with what we expect from common sense, and it encourages us to challenge our intuitions. One of the most curious things about the birthday paradox is how it's often met with disbelief. It's one of those mathematical results that, once understood, seems so obvious, yet at first, it feels almost impossible. It challenges our understanding of randomness, and helps us see how probability operates in the real world, not just in abstract terms. It's a perfect example of how even the most straightforward-seeming problems can lead to surprising insights. The birthday paradox also serves as a reminder of the elegance of mathematical thinking. It shows us that by understanding how combinations and probabilities work together, we can uncover patterns and truths that would otherwise remain hidden. It's a beautiful example of how mathematics allows us to break through the surface-level assumptions and discover the deeper hidden relationships at play. By the time we come to terms with the paradox, we've not only learned something about probability, but we've also gained a new perspective on how we interpret chance and randomness in our daily lives. The birthday paradox encourages us to think more critically and carefully about the world of probability, and it reminds us that sometimes, what feels most intuitive is actually the thing we need to question the most. Time dilation in relativity is one of the most mind-bending and counterintuitive aspects of Einstein's theory of special relativity. It tells us that time doesn't pass at the same rate for everyone everywhere. It can actually move slower or faster depending on how fast you're moving relative to someone else. This concept challenges our everyday experience of time as a constant steady flow unaffected by the world around us. But in the world of relativity, time is far more flexible than we might expect. At its core, time dilation occurs when an object moves at a speed close to the speed of light, causing time for that object to appear to slow down relative to an observer who is at rest. This is because, according to Einstein's special theory of relativity, the speed of light is always constant, no matter how fast the observer is moving. As an object approaches the speed of light, the faster it moves, the more time slows down for it, as experienced by an outside observer. This means that from the perspective of someone who is stationary, a fast-moving object will experience time more slowly than they do. The idea of time slowing down can be difficult to grasp, because it contradicts our usual experience of time as something that flows equally for everyone, no matter how fast they are moving. But special relativity tells us that time is relative. It's not an absolute constant. The faster you move, the more pronounced this effect becomes. In fact, if you could somehow travel at the speed of light, which according to the theory, is impossible for anything with mass, time would stop entirely for you. One way to imagine this is to think of two twins. One stays on Earth and the other goes on a journey through space at a high speed. When the traveling twin returns, they would be younger than the twin who stayed behind. This is known as the twin paradox, a thought experiment that illustrates the effects of time dilation. The traveling twin's clock ticks slower during their journey, while the clock of the twin on Earth ticks normally. When they reunite, the time difference between them is a direct result of time dilation caused by the high-speed travel. The phenomenon of time dilation has been experimentally verified, too. In fact, the accuracy of GPS satellites depends on a correction for time dilation. These satellites are moving at high speeds relative to the Earth's surface, and because of this, their onboard clocks tick slightly faster than clocks on Earth. Engineers have to account for this difference when synchronizing satellite signals with ground-based systems. So while it might seem like something out of science fiction, time dilation is something we encounter in practical real-world technology. Time dilation also has profound implications for our understanding of space and time itself. In relativity, space and time are not separate entities. They are intertwined into what is called space-time. The faster we move through space, the slower we move through time, and this connection is what makes the concept of time dilation possible. It's a dramatic departure from the Newtonian view of time as a universal ticking clock, and it shows us how deeply our perception of reality can be altered when we move at high velocities or in strong gravitational fields. This effect of time dilation isn't just theoretical. It's also practical in the realm of high-energy particles. For example, cosmic rays, high-energy particles from space, travel at speeds close to the speed of light, and they have been observed to live much longer than they would if they were stationary, as a result of time dilation. Their decay rate is slower because from our perspective on Earth, their time has slowed down. The most fascinating part of time dilation is the way it reshapes our understanding of the passage of time itself. It suggests that time is not something fixed and unchanging, but is instead something that can stretch and contract depending on how we move through space. The faster we go, the more we experience time differently, revealing that time, much like space, is malleable, not the rigid, unchangeable force we might have thought it to be. This phenomenon brings us face to face with the astonishing truth that reality, at its core, is far more flexible than we might imagine. The rules of time and space are not the same everywhere, and they change based on our motion and position in the universe. Time dilation doesn't just ask us to rethink how we perceive time. It challenges us to reconsider our place in the universe itself. We're not passive observers, merely drifting along through time. We're active participants, shaping and bending time with every motion we make. Hilbert's Grand Hotel is a fascinating thought experiment that reveals the strange, mind-bending nature of infinity. This paradox, imagined by the German mathematician David Hilbert, takes the concept of an infinitely large hotel to explore how the infinite can behave in ways that seem utterly counterintuitive. Imagine a hotel with infinitely many rooms, each one occupied by a guest. At first glance, this might seem like a situation where no more guests can be accommodated, since every room is already taken. But in the realm of infinite sets, things work very differently. In Hilbert's Grand Hotel, even though all the rooms are full, there is still room for more guests. This is because infinity isn't like a regular number. It doesn't behave the way we intuitively expect. If a new guest arrives, the hotel can simply ask the guest in room 1 to move to room 2, the guest in room 2 to move to room 3, and so on, with each guest moving to the next room. By doing this, room 1 becomes free for the new guest, even though all the rooms were originally occupied. This simple move reveals how the infinite can accommodate additions without limit, and it challenges our understanding of what full means. Hilbert's Grand Hotel doesn't stop there. Imagine that an infinite number of new guests arrive at the hotel, an infinite busload of people, each looking for a room. At first it might seem like there's no room for all these new guests, since all the rooms are occupied. But once again, the hotel can make space by using the same trick. Ask the guest in room 1 to move to room 2, the guest in room 2 to move to room 4, the guest in room 3 to move to room 6, and so on. In this way, all the odd-numbered rooms are freed up, and an infinite number of new guests can be accommodated, even though there were already an infinite number of people there to begin with. This paradox also extends to situations involving infinite subsets. For example, imagine that an infinite number of new guests arrive, but this time they are not from just one bus but from an entire fleet. The hotel still has a solution. It could shift every guest in a way that frees up infinitely many rooms for the new arrivals. Through clever rearrangements, the hotel can always accommodate more guests, regardless of how many arrive, because infinity doesn't behave like a finite number. Hilbert's Grand Hotel provides a striking illustration of how infinite sets can behave in strange and surprising ways. It challenges our intuition about size and space, showing us that even something that seems full or complete, like an infinite hotel, can still make room for more, no matter how many guests arrive. This paradox forces us to reconsider what we mean by full or occupied when dealing with the infinite, because the usual rules that govern finite sets simply don't apply. The true power of Hilbert's thought experiment lies in how it reshapes our understanding of infinity. We tend to think of infinity as something absolute, something that can't be added to or subtracted from. But Hilbert's Grand Hotel reveals that infinity is not a single, unchangeable concept. Rather, it is a dynamic and flexible idea that can accommodate an endless number of additions, subtractions, and rearrangements. This idea has profound implications for mathematics, particularly in set theory and the study of infinite sets, where the notions of size and comparison are far more complex than we typically imagine. The paradox is also a reminder of how deeply counterintuitive the world of infinity is. When we step into the realm of infinite sets, our everyday experiences and expectations break down. What seems impossible in the finite world, like adding more people to a completely full hotel, becomes not only possible but trivial in the context of infinity. Hilbert's Grand Hotel helps us to see that infinity is not just a large number, but a concept that stretches and bends in ways that challenge our deepest assumptions about the nature of reality. In the world of Hilbert's Grand Hotel, there is always room for more. And as strange as that may seem, this paradox serves as a beautiful reminder of the infinite possibilities that lie within the abstract mathematical world, where the boundaries of space, size, and logic are only limited by our imaginations. The Monty Hall problem is a classic paradox from probability theory that challenges our intuition in a way that can seem almost impossible to believe. It's based on a game show scenario where a contestant is faced with 3 doors, behind one of which is a grand prize, and behind the others, a goat. The contestant is asked to choose one of the 3 doors. Once they make their choice, The host, Monty Hall, who knows what's behind each door, opens one of the remaining doors, revealing a goat. The contestant is then given the option to stick with their original choice, or switch to the other unopened door. The question is, should they stick with their first choice, or is it in their best interest to switch? At first glance, it seems like it shouldn't matter whether the contestant switches or not. After all, there are 2 doors left, and so it seems like the odds of winning the prize should be 50-50ths, right? But that's exactly where our intuition fails us. The reality is, the contestant should always switch, because doing so actually gives them a better chance of winning. A 2 in 3 chance, as opposed to the 1 in 3 chance they have, if they stick with their original choice. Let's break it down. When the contestant first chooses a door, there's a 1 in 3 chance that they've picked the door with the prize, and a 2 in 3 chance that the prize is behind one of the other 2 doors. Now, Monty opens one of the remaining doors to reveal a goat, but importantly, he will never open the door with the prize. This action doesn't change the fact that initially, there's a 2 in 3 chance that the prize is behind one of the other 2 doors. By switching, the contestant essentially bets that their first choice was wrong, which given the initial odds, is more likely to be the case. The key to the problem is that Monty's knowledge of what's behind the doors and his actions, opening a door with a goat, give the contestant valuable information. If the contestant switches, they are actually taking advantage of that information, making it more likely that they will win. To visualize this, imagine that the contestant first picks a door, and behind it is a goat. Monty then opens one of the remaining doors to reveal another goat. The contestant can now switch to the last door, which must have the prize. In this scenario, switching wins the prize. But if the contestant's initial pick was correct, switching would lead them to a goat. While that might sound like a 50-50th choice, it's important to remember that, initially, there was a 2 in 3 chance of picking a goat, not the prize. So, by switching, the contestant is essentially betting that they picked wrong, which, statistically speaking, is the better bet. The Monty Hall problem is a perfect example of how probability can defy our everyday expectations. Our intuition leads us to believe that the odds are always 50-50ths after Monty opens a door, but the actual odds are stacked in favor of switching. The problem highlights the way in which our brains often struggle to understand probabilistic reasoning, especially when we are confronted with unfamiliar or counterintuitive scenarios. One of the fascinating aspects of this paradox is how it remains so puzzling, even though the math behind it is relatively simple. Many people, including professional mathematicians, have been initially fooled by the apparent 50-50ths odds, only to be shocked when they discover that switching really is the optimal strategy. This has led to countless debates and experiments, but despite the confusion it generates, the Monty Hall problem remains an elegant demonstration of how probability can produce surprising outcomes that defy our natural reasoning. By examining the Monty Hall problem, we can gain deeper insight into how we approach decision-making, particularly when faced with uncertainty and incomplete information. It serves as a reminder that our intuitions are not always reliable when it comes to probability, and that sometimes, the most logical choice may feel counterintuitive or even strange. The lesson here is that our instincts about risk, chance, and probability don't always align with the reality of the situation, but with a little mathematical insight, we can learn to navigate these paradoxes with greater clarity. The Coastline Paradox is a fascinating exploration of how our intuition about distance and measurement can be dramatically different when we deal with irregular shapes and the concept of infinity. The paradox begins with a simple observation. The length of a coastline seems easy to measure, right? You just take a ruler and measure along the shore, and you have the distance. But when you try to measure the coastline of a landmass with a jagged winding shoreline, things get a lot more complicated, and what seems like a straightforward task turns into a mathematical mystery. The paradox emerges when you realize that the length of the coastline depends on the size of the measurement unit you use. Imagine you're measuring the coastline of a country like the United Kingdom. If you use a large measurement unit, say a kilometer, you'll estimate the coastline's length by measuring the straight-line distances between points on the shore. This will give you a relatively smooth, rough estimate of the coastline's length. But if you use smaller units, like meters or even centimeters, the total length seems to increase because you are measuring all the tiny twists and turns along the shore that were ignored in the larger scale measurement. The more finely you measure, the longer the coastline appears to be. This is because the jagged, irregular nature of the coastline means that smaller measurement units capture more of the fine details, revealing new curves and edges that weren't visible at larger scales. As a result, the length of the coastline can grow indefinitely the smaller the units you use, leading to the paradox. If you keep decreasing the size of the units, you end up with a length that seems to approach infinity. This paradox challenges our intuitive ideas about measurement and distance. We are accustomed to thinking of lengths as fixed quantities, where a longer measurement just means more distance. But in the case of coastlines, the true length depends on how we choose to measure it, and this can lead to a situation where the length of a coastline is not well defined, or at least not a fixed number. The coastline paradox has deep implications in mathematics, particularly in the field of fractals. A fractal is a complex geometric shape that looks similar at every scale, meaning the pattern repeats itself infinitely as you zoom in. The coastline paradox is often used as an example of a fractal, because coastlines are irregular and jagged, with new details appearing at every level of magnification. This self-similar structure, the idea that coastlines are never truly smooth or straight, no matter how closely you look, lies at the heart of the paradox. The paradox also has real-world implications. In practical terms, if you want to accurately measure the coastline of a country, or even a small island, you need to decide on a method of measurement. Depending on how you do it, the result could vary greatly. While this might seem like a problem only for mathematicians, it has practical consequences in fields like geography, cartography, and environmental science, where accurate measurements of land and sea borders are often crucial. The coastline paradox is an excellent example of how mathematics can reveal unexpected complexities hidden within seemingly simple ideas. It also challenges our traditional notions of space and measurement, showing that even familiar concepts like length and distance can behave in strange and counterintuitive ways when we start to explore them in greater detail. When we zoom in on the tiny details of an irregular shape, like a coastline, we uncover a complexity that seems to defy our usual expectations. This paradox forces us to reconsider what we really mean when we say something is measured, and it opens our eyes to the rich fractal nature of the world around us. At its core, the coastline paradox invites us to think more deeply about the nature of measurement, scale, and the infinite. It challenges our assumptions about the physical world, revealing that even the simplest objects, like a coastline, can be far more complicated than we might initially believe. Through this paradox, we see how mathematics can help us explore the intricate patterns that govern nature, and how our understanding of the world can shift when we embrace the true complexity of the spaces we inhabit. The Banach-Tarski Paradox is one of the most mind-boggling and counterintuitive results in modern mathematics, and it reveals the strange and sometimes bizarre nature of infinite sets and the concept of geometric space. The paradox suggests that it is theoretically possible to take a solid sphere. Imagine, for instance, a perfectly smooth three-dimensional ball, and using only rotations and translations, break it into a finite number of disjoint pieces, and then reassemble those pieces into two identical spheres, each the same size as the original. The result is nothing short of astonishing. Starting with one sphere, you can create two identical spheres. How can that be possible? Doesn't this violate basic principles of physics and the conservation of volume? At its heart, the Banach-Tarski Paradox is a result of the peculiar properties of infinite sets. It fundamentally relies on a mathematical concept known as the axiom of choice, a powerful yet controversial principle in set theory. This axiom allows mathematicians to make arbitrary selections from an infinite collection of sets, even when there is no explicit rule to guide those choices. In this paradox, the axiom enables the selection of points from a sphere in such a way that, when the sphere is divided into parts, the pieces are so bizarre and non-measurable that they defy our standard notions of geometry and volume. The pieces created in the Banach-Tarski construction are not ordinary pieces. They are highly fragmented and infinitely complex. These pieces do not have well-defined sizes in the way we usually think about them. They are non-measurable sets, which means that the standard tools we use to measure the size or volume of objects, things like length, area, or volume, simply don't apply to them. In fact, the pieces themselves are so wild that it's impossible to physically recreate them with any process, since they exist purely in the realm of abstract mathematics. One of the key ideas behind the paradox is that the geometry involved is not something we encounter in the real world. The paradox exists purely in the abstract mathematical world. No physical sphere can be decomposed and rearranged in the way that the Banach-Tarski Paradox suggests. This distinction between mathematical abstraction and physical reality is crucial. While the mathematics behind the paradox is valid and logically consistent, it's important to recognize that the result does not translate into any real-world scenario. If you tried to apply the paradox to actual physical objects, it would not work. The reason is that in the real world, objects have measurable, finite sizes, and are made up of a finite number of particles. No physical process could allow you to cut and rearrange an object in the way the paradox suggests. The proof of the Banach-Tarski paradox involves concepts from several branches of advanced mathematics, particularly group theory and measure theory. It leverages the idea that the group of rotations in three-dimensional space contains subgroups that behave in such a way that they allow for this paradoxical decomposition of the sphere. Specifically, the paradox hinges on the existence of free groups, which are groups that exhibit certain properties that allow for these weird and non-intuitive decompositions. It is the non-immutability of these groups, a technical property that makes them resistant to measuring in a conventional sense, that enables this seemingly impossible result. Though the Banach-Tarski paradox is mathematically valid, it has sparked heated debates among mathematicians and philosophers. One of the major points of contention is the axiom of choice itself, as it allows for these non-constructive processes that seem to lead to physically impossible outcomes. Some argue that the axiom should be questioned because it gives rise to phenomena like the Banach-Tarski paradox, while others defend its usefulness, pointing out that it has countless applications in other areas of mathematics, where its consequences are desirable, and lead to results that are both practical and elegant. This paradox also raises deeper questions about the nature of space, volume, and infinity. It forces us to reconsider our intuitive ideas about what is real and what exists only in mathematical abstraction. The Banach-Tarski paradox challenges our understanding of how the world works by showing us that even the simplest objects, like a sphere, can behave in ways that seem entirely disconnected from our everyday experience. The idea that a single object can be split and reassembled into two identical objects, even in theory, is a reminder of how strange and counterintuitive mathematics can be when we delve into the abstract. The Banach-Tarski paradox doesn't just defy our expectations about volume and conservation. It serves as a profound illustration of the gap that often exists between the physical world and the world of pure mathematics. By pushing the boundaries of what we think is possible, the paradox invites us to expand our understanding of both mathematics and reality, and to appreciate the extraordinary complexity that lies within even the simplest geometric concepts.